Hello there, and welcome to Just About Earth, where curiosity gets cozy and science takes its time to settle in. Tonight we're not chasing the ticking of clocks or the whirring of machines. We're heading backward, far backward, into an age when the world itself was still learning how to breathe in unison. The story waiting for us isn't one of people or cities, but of continents drifting slowly toward each other, drawn together by forces so vast and patient that a lifetime would barely count as a heartbeat to them. This is the tale of how the land beneath your feet, the rocks and soil that hold every city and mountain you know, were once pieces of a great puzzle that fit perfectly together. We're going to visit the time when that puzzle was finally complete, when all the scattered lands of Earth joined hands and became one, the time of Pangea. Before we set off, take a moment to feel where you are. Maybe you're listening as night falls, or maybe it's the middle of the afternoon where you are, sunlight pouring across your room. Either way, you and I are standing on one small fragment of that ancient world. A piece that drifted apart long after the story we're about to tell. It's a quiet thought that we're sitting here on the remains of a supercontinent, still moving very slowly, still part of that endless rhythm. If that thought brings even a hint of wonder or a touch of calm curiosity, I'd be grateful if you gave this video a like, or perhaps subscribed. It helps this little corner of quiet science reach others who might need a moment of stillness too. Now settle in. Let your thoughts slow down. We're going to take our time. Because the world we're about to visit didn't rush either. The story of Pangea begins long before its name was ever spoken. Back then, the continents didn't even exist in the form we know them today. The planet was a shifting mosaic of islands, mountain belts, and shallow seas. What we call Earth's crust was already restless, carried along by immense convection currents deep in the mantle. You might picture the planet's interior like a pot of thick stew simmering slowly over a low flame. Material rises where it's hot, cools, and sinks again, carrying the solid plates above in an unending dance. Over hundreds of millions of years, this slow motion gave rise to oceans and continents that drifted, collided, and tore apart again. It's a movement so slow it might as well be still from our perspective, but over geological time it changes everything. When we talk about Pangea's birth, we're really talking about a long reunion. The continents had come together before, in other configurations. Scientists have names for those older worlds, Rodinia, Nuna, and others. But Pangea was the last great supercontinent before the modern world began to form. It came together during the late Carboniferous and early Permian periods, somewhere around 300 million years ago. Imagine the scattered pieces of land, Laurasia in the north, Gondwana in the south, slowly converging. Bit by bit, the gaps between them closed. Oceans that had stretched wide for millions of years shrank away. As they vanished, mountain chains rose where the edges collided, forming new highlands that once towered like young versions of the Himalayas. Somewhere in the middle of all that movement, Pangea emerged, an immense continent stretching nearly from pole to pole. It's difficult to grasp just how enormous it was. If you could stand in its centre, you might travel for weeks without seeing the sea. The interior was so vast that moisture from the coast rarely reached it. That meant long, dry seasons, hot days, cold nights, and endless deserts that stretched farther than any modern horizon. The air itself would have carried a different balance of gases than what we breathe today. Oxygen levels fluctuated. The winds shifted across wide basins. The world's climate didn't just change from year to year. It transformed slowly across epochs, sometimes leaning toward warmth and dryness, sometimes toward ice. But always, it was alive. The creatures of that time were living through one of Earth's most dramatic transitions. The Carboniferous had been an age of swamps and dense forests, of giant ferns and tree-sized horsetails, and of enormous insects that thrived in oxygen-rich air. By the time Pangea came together, much of that lush greenery began to fade. As the climate grew drier, the swamp forests withered, giving way to hardier plants, conifers, seed ferns, and other species that could survive in the new arid landscapes. The shift in vegetation changed the course of evolution for nearly everything that lived on land. The insects adapted, reptiles diversified, and the first true ancestors of mammals began to appear, their warm-blooded bodies learning to handle the changing world. The surface of Pangea was a mosaic of worlds in itself. Around the coasts, forests and river systems flourished, home to amphibians, reptiles and early synapsids. In the interior, the land opened into dusty plains where life had to be tough. Farther north and south, near the poles, the climate could still swing to cold extremes. Ice caps sometimes grew and shrank with the slow rhythm of the planet's orbit and tilt. In every region, life found its own rhythm, a balance between survival and adaptation that mirrored the great tectonic rhythm beneath. The oceans that surrounded Pangea were no less vast than the land itself. To the west and north stretched Panthalassa, the world ocean that wrapped almost entirely around the planet. To the east, the smaller but still immense Tethys Sea lay cradled between converging land masses. These waters were teeming with life. Ammonites drifted in their spiral shells, trilobites were fading but still clung to existence, and early sharks and fish patrolled the depths. Coral reefs rose in warm shallows, though not always the coral we know today. Ancient ragose and tabulate corals built their own forms of reef long before modern species appeared. Every coastline was a meeting point between land and sea, a transition that echoed the joining of continents themselves. When scientists piece together the story of Pangea, they use clues that are scattered across the modern world. Fossils of the same species appear on continents now separated by thousands of kilometres. Layers of rock match across oceans. The shapes of the continents, when pushed together on a map, fit like parts of an ancient puzzle. It was a German meteorologist named Alfred Wegener who, in the early 20th century, proposed that these clues all pointed to continental drift. At the time, his idea was met with skepticism. The notion that the continents themselves moved seemed too strange. But over the decades that followed, evidence grew. Paleomagnetism, seafloor spreading, the movement of tectonic plates, and Wegener's vision became one of the cornerstones of modern geology. When we talk about Pangea today, we're standing on the foundation he helped to build. The formation of Pangea wasn't a single event, but a drawn-out process, a series of collisions and closures that reshaped the planet over tens of millions of years. The northern lands of Laurasia formed as North America and Eurasia came together. To the south, Gondwana united what are now South America, Africa, Antarctica, India and Australia. As these two great masses collided, the supercontinent took shape. Mountains rose along their seams, especially across what is now the eastern United States, northern Europe, and parts of Africa. These were the Appalachians, the Urals, and the Mauritaniades in their youth, testament to the force of continents colliding. It's humbling to think that what we now consider distinct continents were once part of a single, unbroken surface. The idea stretches the imagination. The dinosaurs that would later walk the earth were still far in the future. Mammals, birds, and flowering plants didn't yet exist. Even the familiar outlines of the continents we see on a globe were hidden within Pangea's form, waiting to be revealed millions of years later, when it would eventually break apart again. But that's a story for another time. For now, we linger in its creation, in the moment when the Earth was learning what it meant to be whole. The air of the Permian carried dust, warmth, and the faint scent of resin from coniferous forests. Insects buzzed across dry plains, and reptiles basked under a bright sun. Rivers cut through red beds of sediment, their waters carving paths that would one day become fossils themselves. Volcanoes sometimes marked the horizon, their ash settling over valleys, preserving traces of the creatures that passed through. Somewhere a synapsid, one of those early mammal-like reptiles, might have lifted its head and looked across a horizon that seemed endless. It couldn't have known that the land it walks stretched almost from pole to pole, or that millions of years later, that same stretch of ground would be scattered into pieces and carry forests, cities, and oceans far apart. To imagine the world of Pangea is to think in slow motion. Mountains don't rise in an afternoon. Oceans don't close overnight. Every ridge, basin, and valley was shaped by a balance of pressure and time. The crust itself creaked and folded like paper under gentle but relentless hands. The heat from the mantle below pushed against the cool surface, and the continents drifted slowly toward each other, millimetre by millimetre, year after year. In that motion lies one of the planet's most enduring truths, that even the ground beneath us is not still, but part of a living, breathing system that never truly rests. There's something quietly comforting about that thought. The world has been through cycles of joining and separation before. Pangea was not the first supercontinent, and it will not be the last. The same forces that brought it together are still at work, guiding the continents on their gradual paths. Someday, far beyond our lifetimes, a new supercontinent may form again. The Atlantic might close, the Pacific might vanish, the land might gather once more into a single vast expanse, and the Earth will look in its own way, whole again. For now, though, we stay in the Permian, where the story of Pangea is just beginning. The continents are pressed together, the climate is changing, and life is adapting to new conditions. Deep beneath the crust, the mantle stirs with restless energy. The air above carries both life and dust. The oceans are alive with creatures older than any lineage we know. The land is dry, the sky wide, and the world, though silent in its movement, is shifting in ways that will shape every era to come. And somewhere, in that ancient stillness, you can almost feel the heartbeat of the planet slow and steady as Pangea takes its first breath and begins its long reign over the surface of the Earth. The world we live on seems solid beneath our feet, but for most of human history that feeling of permanence was an illusion we never thought to question. Mountains felt eternal, oceans immovable, continents fixed forever in their places. When people looked at maps, they saw the borders of nations, not the scars of a planet that had been drifting, stretching, and colliding for billions of years. It took a long time for us to realise that the land itself moves, that the shapes of continents are snapshots in an endless rearrangement of the Earth's crust. Yet that idea, as extraordinary as it sounds, began with something deceptively simple. Puzzle pieces. Imagine the first time someone noticed that the eastern edge of South America seems to fit against the western curve of Africa. It's almost like they were once one shape, broken apart and gently pulled away. This observation wasn't new, but for centuries it lingered as a curiosity, a coincidence without an explanation. Maps were young and the world was still being charted. The thought that continents could move seemed too bold, too far removed from the familiar notion of a stable Earth. But the resemblance was there, visible to anyone who looked closely. And like most discoveries, it began not with certainty, but with curiosity that refused to fade. The 19th century was a time when science was busy cataloguing everything it could. Minerals, fossils, layers of rock stacked in neat columns across the pages of geology books. In that quiet accumulation of facts, a few patterns began to emerge. Identical fossils turned up on coastlines separated by vast oceans. Ancient rock formations matched like halves of a torn page. Coal beds in North America had perfect twins in Europe. Species that could never have crossed an ocean on their own appeared on distant shores as if they had once shared the same land. Each new clue was small on its own, but together they formed something strange, something that didn't fit the fixed Earth picture that most scientists held. Among those who noticed was Alfred Wegener, a German meteorologist who spent his career studying weather patterns, polar air currents, and the mechanics of the atmosphere. He was not a geologist by training, which perhaps helped him see the problem from an unexpected angle. In 1912, he proposed a radical idea. The continents were once joined together in a single massive landmass, which he called Pangea. Over millions of years, he said, they drifted apart, carried by forces deep within the Earth. He published his theory a few years later, calling it continental drift. To him, it explained the matching fossils, the similar rock layers, the way the continents seemed to fit like puzzle pieces pulled slightly apart. The evidence made sense together in a way it hadn't before, but the world of early 20th century science was not ready for such an idea. The Earth to most geologists of the time was seen as solid and immovable, mountains formed through uplift and erosion, not the slow shuffling of continents. Oceans were permanent fixtures, not temporary spaces between drifting plates. Wegener's idea was seen as imaginative but unsupported. The biggest question critics asked was simple: if the continents move, what pushes them? Wegener couldn't answer that. He proposed that maybe the centrifugal force of Earth's rotation or tidal forces from the Moon could be responsible, but his mechanisms didn't work mathematically. Without a clear physical explanation, his theory remained an elegant story that most dismissed. And so, for decades, it lingered on the fringes of science, like a whisper that wouldn't go away. Still, the clues didn't stop appearing. As more rock layers were studied and more fossils unearthed, the patterns became harder to ignore. Across the southern continents, South America, Africa, India, Antarctica and Australia, scientists found evidence of the same ancient plant, Glossopteris. This fern-like species couldn't have crossed oceans, yet its fossils appeared in all those distant lands. Even stranger were the glacial scratches carved into ancient bedrock, pointing to ice sheets that once spread across what are now tropical regions. The direction of the scratches made sense only if those continents had once been joined near the South Pole and later moved to their current positions. Slowly, the old certainty of a static Earth began to weaken. Beneath the surface, another discovery was brewing, one that would finally explain how the continents moved. In the mid-20th century, scientists began mapping the ocean floor using sonar, originally developed for naval purposes during World War II. What they found was startling. The ocean wasn't flat and featureless as once assumed. It was laced with enormous ridges, mountain chains running through the middle of oceans, stretching for tens of thousands of kilometers. At these mid-ocean ridges, molten rock was rising from below the crust, cooling and forming new seafloor. As more material emerged, it pushed the older crust outward. On the opposite sides of oceans, deep trenches marked places where old crust was being pulled down into the mantle. The Earth, it turned out, was recycling its surface, creating and consuming crust in an endless loop. This process, known as seafloor spreading, provided the missing piece Wegener never had, the engine behind continental drift. The continents weren't drifting by themselves. They were passengers riding on massive plates that floated atop the viscous mantle. The planet wasn't static at all. It was dynamic, restless, alive with movement so slow we could never see it happen, yet powerful enough to rearrange the face of the Earth. By the 1960s, the theory of plate tectonics emerged, uniting geology, seismology, and oceanography into one framework. Wegener, who had died decades earlier during an expedition in Greenland, was finally vindicated. The puzzle of continents had been solved, but to truly understand what that means, it helps to imagine the Earth not as a globe of fixed land and sea, but as a living system constantly reshaping itself. The crust we stand on is only a thin shell compared to the molten flowing rock beneath. Where plates meet, the Earth either builds or destroys. Some boundaries create new land, others swallow it. Along ridges, magma rises and cools, forming new crust. Along trenches, old crust sinks back into the mantle, melting into heat and pressure. The continents are thicker and lighter, floating like rafts on this sea of solid flow. Over time, they move toward or away from one another, their collisions forming mountains, their separations forming new oceans. The patterns of these movements form cycles that span hundreds of millions of years. One of these cycles is called the supercontinent cycle. the recurring formation and breakup of massive land masses over geological time. Pangea was one of the latest in this sequence, but not the first. Before it, there were others, each formed and broken by the same deep forces. Each time, the planet's geography, climate, and life evolved in response. The continents might seem independent, but they are parts of a single system connected by heat flow, gravity, and the slow churn of the mantle below. When they come together, global climates change, ocean currents shift, species evolve or disappear. When they break apart, new coastlines appear, new habitats form, and the story begins again. When the continents that would form Pangea started drifting toward each other, the world was entering the late Paleozoic era. Land plants were spreading, animals were adapting to life away from water, and atmospheric oxygen levels were high. The stage was set for transformation. The northern lands, including what we now call North America and Eurasia, began to close the ocean between them. The southern continents, grouped as Gondwana, moved northward. Between them, a long stretch of ocean known as the Rake began to disappear. The collisions that followed created vast mountain ranges and restructured the entire planet's geography. Each collision didn't happen in a day or even a lifetime. It took millions of years. To the Earth, time is a slow current, and each movement of the crust is a ripple on its surface. The forces at work were both immense and subtle. Beneath the crust, convection currents in the mantle shifted heat outward. Above, erosion carried sediment into basins, where pressure turned it into rock. Volcanoes mark the boundaries of collision zones, releasing gases that altered the atmosphere. Every grain of sand, every layer of shale and limestone, every fossilized leaf recorded part of this process. When scientists today study those layers, they're reading the archives of the planet, pages written not in ink but in minerals and pressure. In that record, we find evidence of the continent's motion, a record so precise it can trace not just their shapes, but their ancient positions, measured by the magnetic minerals that align with Earth's field as they cool. Those tiny alignments, frozen in stone, are compass needles pointing toward a vanished world. The idea that continents are in constant motion changed how we see everything. Geography became a dynamic process rather than a static backdrop. Mountains were no longer eternal. They rose and fell like waves, given enough time. Ocean basins opened and closed. Islands formed and disappeared. Even the air we breathe, the distribution of life, and the patterns of climate, all of it tied to the slow drifting of the continents. Pangea wasn't just a geological curiosity. It was the centerpiece of one of Earth's greatest transformations. To visualize it, imagine the planet from far above. The scattered continents of an earlier age begin to move, imperceptibly but inevitably, drawn by invisible currents. Over tens of millions of years they inch closer. Oceans narrow, islands collide, mountains rise. Bit by bit, the land unites into a single mass. From the poles to the equator, a continuous stretch of rock and soil covers much of the planet's surface. Around it, one vast ocean flows, carrying storms and tides that circle the world. The continents, once isolated, now share a single climate system, a single biosphere connected by land. That unity changes everything, from the pattern of winds to the evolution of species. It's a transformation that can't be seen in human time, yet its consequences ripple through every layer of Earth's history. And even now, long after Pangea broke apart, the traces remain. The Appalachian Mountains in North America, the Caledonian Ranges in Europe, and the ranges of North Africa all share the same origin, formed when the continents collided during Pangea's assembly. The rocks in those mountains tell the same story, the same sequence of pressures, the same kinds of minerals. They are remnants of that great puzzle, reminders of a time when the world was one. The fossils within them link life across oceans, echoing the unity that once existed. Every ridge and basin is a piece of that map, a fragment of the moment when the Earth gathered itself together, Continental drift is no longer theory, but the quiet fact that defines our planet's surface. The continents continue to move today at rates of just a few centimetres per year. You can't feel it under your feet, but it's happening. Australia drifting north, Africa inching into Europe, the Atlantic widening slowly year after year. In millions of years, the Earth will look completely different again. New mountains will rise, new seas will form. The pieces of the puzzle will rearrange once more, as they always have. When we talk about Pangea's birth, we're really tracing one chapter in that long cycle, one moment when the Earth drew its scattered pieces together. The puzzle of continents is more than geology. It's the story of movement, connection, and change. Every grain of sand you've ever touched was once part of something older, carried from mountain to river, from continent to sea. The ground beneath you has travelled farther than you can imagine, across oceans through heat and pressure, folded and unfolded by time itself. The continents have always been moving, and so, in a quiet way, has everything else. As Pangea took shape, the planet began to feel the effects of its new arrangement. The oceans narrowed, the air changed, the world's climate adjusted to the sheer size of this new landmass. It was the start of something enormous, a global experiment in heat, dryness, and survival. And somewhere on that vast, united Earth, the first creatures were learning how to live in a world that had never existed before, under skies that stretched unbroken from horizon to horizon across a continent the size of the world itself. Before the continents came together, the Earth looked nothing like the world we know. The land was scattered across the globe in fragments, drifting on the slow currents of the planet's mantle, each piece carrying its own climate, forests and creatures. The seas between them were wide and deep, filled with ancient life that had never seen the shores of another continent. If you could look down at the planet from above during that time, you would see something that felt strangely familiar and yet entirely alien, a jigsaw of continents still in motion, waiting for gravity and heat to nudge them into the embrace that would form Pangea. The story begins near the end of the Carboniferous period, around 320 million years ago. Much of the planet was warm, humid, and alive with green. Vast tropical forests stretched across what would one day become North America and Europe, forming endless swamps filled with towering plants and strange amphibians. The air was rich in oxygen, so thick with it that insects grew to enormous sizes. Dragonflies had wings as wide as a modern hawk's. Millipedes longer than a person crawled through the undergrowth, and the forests themselves breathed in great waves of mist and vapour. It was a world driven by heat and moisture, where every breath carried the scent of decay and growth, and every sound echoed across shallow waters and dense vegetation. At this time, the land was not yet one. The continents existed as a loose collection of drifting plates. In the north lay Laurasia, made up of what would become North America, Europe, and parts of Asia. In the south was Gondwana, a vast continent containing the land that would one day separate into South America, Africa, Antarctica, Australia, and India. Between them stretched the Reich Ocean, a wide expanse of water that had existed for millions of years. Smaller pieces of land floated between them, colliding and fusing in slow motion. These collisions built mountain ranges that would one day weather into familiar ridges, the foundations of future landscapes. If you could have walked the Earth in that era, you would have crossed landscapes that felt strange and yet recognisable in small ways. On some continents, thick coal forests flourished, where tree-like plants grew with trunks of fibrous bark and leaves arranged like scales. On others, broad floodplains were crossed by winding rivers, carrying silt and plant debris that would later become the coal seams we mine today. The air would have been damp and heavy. The light filtered through thick canopies, insects moving in slow, deliberate paths. The soundscape would have been filled with the gentle trickle of water, the buzz of wings, and the croaks of early amphibians resting at the edges of ancient ponds. As Laurasia and Gondwana drifted closer, smaller land masses known as microcontinents began to vanish into the spaces between them. One by one, they collided with the larger plates, closing the oceans that had once separated them. These movements were not fast or violent in the human sense. They unfolded over tens of millions of years, driven by the invisible movement of molten rock beneath the crust. At the surface, the effect was gradual. The slow rising of mountains, the shifting of rivers, the quiet change in the tilt of land. In some regions, volcanoes marked the boundaries, releasing ash and gases into the atmosphere, altering the global climate in subtle but lasting ways. The continents themselves were mosaics of environments. In the far south, near the pole, ice sheets had begun to form. Gondwana carried large glaciers across parts of what are now South Africa, India and South America. The marks of these ice sheets, scratches and grooves carved into bedrock, still exist today, frozen in stone as reminders of that ancient cold. The ice advanced and retreated in cycles that mirrored changes in the planet's orbit, tilting Earth slightly toward or away from the Sun over spans of hundreds of thousands of years. Each cycle left traces in sedimentary layers, a rhythm written in a rock. While the southern lands were frozen, the equatorial regions were dense with heat and life. There, rain fell in endless cycles, feeding rivers that meandered through forests of leucopsids and horsetails. The plants of the Carboniferous were not yet true trees, but something between giant ferns and conifers, using spores instead of seeds to reproduce. They grew tall and close together, their roots forming tangled mats that trapped sediment and created swampy ground. When these plants died, they fell into the still waters of the swamps, buried by new growth before they could fully decay. Layer upon layer of this material built up over millions of years, compressed under pressure and heat, eventually turning into the coal that now powers modern industry. Every spark of coal burned today is a fragment of that ancient forest, a relic of the time before Pangea. Life in the oceans was just as diverse. The seas between the drifting continents were full of trilobites, brachiopods, crinoids, ammonites, and fish with armoured scales. Coral reefs flourished in the shallows, built not by modern corals but by earlier forms that thrived in warm, clear waters. The open ocean teemed with plankton and free-swimming predators, while the seafloor was covered in shellfish and burrowing creatures. Sharks and early ray-finned fish dominated the food chains. Above them all, the rhythm of the tides moved with the pull of the moon, just as it does today. The only difference was the placement of the continents, the direction of the currents, and the species that swam through them. In this fragmented world, the Earth's climate was divided into zones as distinct as separate worlds. Near the equator, humidity fed the dense forests. Farther north and south, drier climates prevailed, with stretches of desert forming in the interiors of some continents. The glacial regions at the southern edge of Gondwana brought cold air that shaped wind and rainfall across the planet. The collision of land masses influenced air currents and ocean circulation, setting the stage for the massive shifts that would come once Pangea formed. In a sense, the planet was preparing itself for the next transformation. Each continental collision changed not only the land but also life itself. When two land masses met, species that had evolved separately suddenly found themselves sharing the same ecosystems. This mixing of life led to bursts of evolution and extinction. Amphibians, which had once been the dominant land vertebrates, began to face competition from a new kind of creature, the early reptiles. These animals, with their tough scaly skin and eggs that could survive out of water, were better suited for drier environments. They spread across the continents, adapting to new climates and paving the way for the reptiles that would later rule the Mesozoic era. The first ancestors of mammals appeared during this time too, small and resilient, part of a lineage that would quietly persist through every extinction that followed. The closing of oceans also meant the formation of new mountains. When continents collided, their edges crumpled and folded, forcing rocks upward into vast ranges. The collision of Gondwana with Laurasia would eventually form the Appalachians in North America and the Ural Mountains in Russia. To the south, the formation of Pangea's core brought together Africa, South America and Antarctica, raising highlands that changed rainfall patterns for millions of years. These mountains eroded slowly, their sediments carried away by rivers and deposited in basins where new life would take hold. The mountains rose and fell, but the memory of their creation stayed written in the rocks they left behind. In the far north, shallow seas covered large portions of what would later become Europe and Asia. These seas were warm and rich with marine life. The continents there were slowly drifting toward the equator, their climates growing milder as they approached lower latitudes. In the southern hemisphere, parts of Gondwana remained cold, shaped by glaciers and the slow movement of ice. The planet was a patchwork of extremes, lush and frozen, wet and dry, life thriving in every corner where conditions allowed. The connection between land and sea, heat and cold, movement and stillness defined this era. As the Carboniferous gave way to the early Permian, the Earth began to change more dramatically. The humid forests of the past began to decline. Global temperatures rose as the continents moved closer together, disrupting ocean currents and reducing rainfall in many areas. The great coal forests started to die back, replaced by plants that could survive in drier, more variable climates. Conifers and seed ferns spread, their tough seeds allowing them to thrive where spore-bearing plants could not. Insects adapted, reptiles expanded their range, and amphibians retreated to wetter refuges near lakes and rivers. The biosphere was adjusting to a drier, harsher Earth, the kind that would soon define the heart of Pangea. Beneath the surface, the mantle continued its slow churn. The energy driving the continents came from deep within the planet, from the heat left over from Earth's formation and the decay of radioactive elements. Convection currents rose and fell like the breath of the planet, carrying the plates above them. These movements didn't just shape geography, they shaped the conditions for life. By changing the positions of continents, they altered sunlight distribution, rainfall, and temperature. Over millions of years, they sculpted the environments that determined which species would thrive and which would vanish. Every shift in the crust rippled upward into the living world. The world before Pangea was not peaceful, but it was balanced in its own way. Each continent held its own ecosystems, its own weather patterns, its own evolving story. The boundaries between land and sea were fluid, moving as sea levels rose and fell. Volcanoes added new land even as erosion wore mountains away. Rivers carved paths that changed course with each uplift and subsidence. The planet was always in motion, but its changes were too slow for any single lifetime to witness. Only in the rocks, in the layers of coal and limestone, in the patterns of fossils could the history be seen. As time passed, the continents drew closer. Laurasia moved southward. Gondwana drifted north. The ocean between them narrowed. The smaller plates that had once separated them vanished into subduction zones, swallowed by the mantle. Mountain ranges rose where the land collided, forming the seams that would one day mark the outline of Pangea. Volcanic arcs burned along those boundaries, their eruptions sending ash into the skies. The climate began to shift again. With the continents closing in, the Earth's system of winds and currents started to reorganize. Where once there had been many small weather systems, soon there would be one vast pattern stretching across a single supercontinent. The planet was on the brink of unification. Even in its scattered state, the Earth before Pangea was remarkable. It was a living experiment in balance, a planet divided into regions, each evolving on its own, yet all connected by the oceans that linked them. The seeds of the future world were already planted. The species that survived this age would inherit a planet transformed. The forests, mountains, and seas of the Carboniferous and early Permian laid the foundation for everything that followed. And though the continents were still separate, The forces beneath them were already working to bring them together quietly, steadily, without pause. The joining of continents was inevitable. It was written into the mechanics of the Earth itself. The same process that had torn apart older supercontinents would now build a new one. The stage was set for the next great act in the planet's history, when the drifting lands would finally meet, the oceans would close, and the world would take on a single face once more. The slow movement of stone and sea was guiding the Earth toward its next identity, a supercontinent that would change everything that lived upon it, a single world made from many, waiting to be born beneath the slow turning of the ancient sun. The continents were moving closer now, though no creature alive then could have sensed it. The oceans between them still stretched wide, yet every year, by mere centimetres, the distance shrank. Mountains grew grain by grain, valleys deepened, rivers changed course. The planet was not still. It was exhaling heat through cracks and ridges that wound invisibly across the sea floor. Deep beneath the crust, the mantle flowed in slow circles, currents of molten rock that rose and sank in motions too vast and steady for any eye to see. It was those silent movements that drove everything, the meeting of continents, the birth of mountains, and the endless rearranging of the Earth's face. When Laurasia and Gondwana finally began to touch, it wasn't sudden or violent in the human sense. It was the slowest collision imaginable, continents moving toward each other like drifting clouds of stone, but in geological time it was a profound moment. The Reich Ocean, which had once stretched wide and blue between them, was folding shut. As the floor of that ocean was dragged beneath the approaching continents, its sediments were crushed, heated, and lifted into rising ridges. The rock that had lain under ancient waters now began its transformation into mountains. Those mountains would one day weather down to dust, but in that moment they were the living edge of the Earth's movement, a frontier between two worlds becoming one. Along those boundaries, heat and pressure reshaped everything. The edges of the colliding plates crumpled like the fabric of a carpet pushed together. Layers of sandstone and shale, once laid down quietly at the bottom of the ocean, were bent and folded into new patterns. Minerals aligned, forming bands and seams that now cut through ancient mountain cores. Granite and basalt intruded upward from below, freezing into solid masses as they cooled. To stand there, had anyone existed to see it, would have been to witness a world in transition, an unending transformation from ocean to mountain, from sediment to stone. At the same time, volcanic activity along the converging margins filled the air with ash and gas. As the oceanic crust slid beneath the continental plates, it melted, sending plumes of magma upward. Volcanoes rose in chains, their eruptions spilling lava and ash across young landscapes. Each eruption changed the air, feeding new gases into the atmosphere. Some cooled the climate temporarily, scattering sunlight. Others warmed it by releasing carbon dioxide trapped in stone. The balance of gases shifted constantly, creating cycles of heat and cold that rippled across the planet. Yet life persisted, adapting as it always had, reshaping itself around the Earth's slow moods. The formation of Pangea was not a single collision, but many. Smaller land masses, microcontinents and island arcs, were caught in the middle, crushed and fused into the growing seams. Each carried its own history of ancient reefs, volcanic chains and coastal plains. As they merged into the larger continents, their rocks became fragments of a greater story. Today, those fragments are found scattered across the world, pieces of once separate lands locked forever into the crust of Pangea's descendants. When geologists study them, they see not just stone, but movement. Every grain of quartz and every band of gneiss is a record of pressure and direction, pointing to the long, patient embrace that created the supercontinent. The mountains that rose from these collisions formed belts thousands of kilometres long. In what would become eastern North America, the collision with Gondwana raised the Appalachians, then towering peaks rivaling the young Himalayas. Across northern Europe and western Russia, the Ural Mountains grew from the same union. In Africa and South America, other ranges rose along the seams, joining the scattered pieces of land into one continuous crust. These mountains didn't appear in a burst of sudden upheaval. They grew inch by inch, year after year, as the Earth's crust folded and broke, then healed again. Erosion wore them down as quickly as new layers rose, balancing creation with decay. The rivers that flowed from their slopes carried sediments to lowlands, building new plains that would one day become homes for evolving life. As the continents pressed together, the world's geography began to transform in every direction. The once separate coastlines fused into continuous stretches of land. Bays became basins. Islands vanished beneath mountain roots. The ocean that remained, the Panthalassa, expanded to cover most of the planet's surface, a single vast body of water surrounding the growing supercontinent. Within that ocean, the currents began to shift. Winds carried heat differently now, and rain fell where it hadn't before. The interior of the land grew dry, shielded from moisture by distance and mountain barriers. What had been green forest along coasts turned to savanna and desert. The world was learning a new pattern of climate guided by the slow motion of stone. The formation of Pangea altered not only the land but also the deep processes of the planet itself. The mantle beneath was affected by the redistribution of weight at the surface. Where the crust thickened under mountain chains, it pressed downward, changing the flow of heat below. This led to the formation of large zones of uplift and subsidence, areas where the crust flexed under its own weight. In those low regions, shallow seas sometimes flooded the land, creating inland basins rich with life. When those seas receded, they left behind thick layers of evaporate salts, gypsum and limestone, records of the time when the sea briefly returned to places that would later stand far from the coast. During the slow collision, earthquakes must have rippled through the growing mountains as stresses built and released. They would have been felt across entire regions, shaking valleys, fracturing rocks and reshaping rivers. Each tremor was part of the earth adjusting to its new shape, releasing the energy that had built up deep underground. Though unseen by any observer, these quakes would have been constant reminders of the planet's movement, small jolts in an otherwise quiet world. Meanwhile, the life that had flourished in the Carboniferous swamps faced challenges. The drying climate and rising mountains disrupted ecosystems that had once stretched across shallow lowlands. The great forests that had produced so much oxygen began to shrink. In their place, hardier plants took root: conifers, cycads, and ginkgos, species that could survive in thinner, drier soils. The amphibians that once dominated rivers and marshes retreated to cooler, wetter areas, while reptiles expanded into the open plains. The formation of Pangea was as much an evolutionary filter as it was a geological event. Those that could adapt to heat and dryness survived. Those that could not slowly disappeared. Across the surface of the growing supercontinent, new patterns of life emerged. In some regions, vast deserts stretched for hundreds of kilometers, marked by red sandstones that still bear the faint imprints of early reptiles and insects. In others, rivers wound through valleys lined with conifers, carrying sediment toward distant seas. The air would have carried the scent of resin and the dry heat of the sun. Dust storms crossed the plains, moving material from one basin to another, slowly building layers that would one day be rock. Each layer told part of the story: the rise of mountains, the shift of winds, the migration of species. The Earth was writing its history in stone. The joining of continents also changed the planet's rotation ever so slightly. When the mass of land moved toward the equator, the distribution of weight altered the Earth's balance, just as a spinning skater changes speed by moving their arms. The days grew marginally longer over millions of years. It was an effect too small to notice in any given lifetime, but it added to the subtle changes that marked the Permian world. The rhythm of day and night remained steady, yet the planet's long-term tempo shifted, one more quiet adjustment in the endless dialogue between surface and core. Volcanic gases from the newly formed mountain belts likely influenced the planet's air chemistry. Sulfur dioxide and carbon dioxide entered the atmosphere through countless small eruptions. Rain absorbed those gases, forming mild acids that weathered rock and returned minerals to the sea. This natural recycling loop maintained the carbon balance that regulated temperature. The Earth, even in its restlessness, remained in equilibrium. The joining of continents, the rise of mountains, and the circulation of gases and minerals were all part of the same process. A global system maintaining itself through change. If you could stand in the middle of Pangea's formation, you would have seen a landscape both familiar and strange. The sky was the same blue, the sun the same golden sphere. But the land beneath was ancient beyond measure. The mountains would have been raw and sharp, newly exposed rock gleaming with minerals. Valleys still filled with volcanic dust, rivers young and fast carving their way through freshly uplifted terrain. The sound of the world would have been different too, a background of rumbling earth, the hiss of vents, the endless sigh of wind across stone. Even the air would have carried a different taste, tinged with the faint sharpness of volcanic gases and the dryness of dust. In this changing environment, life adjusted as it always had. The organisms of the time were not aware of the vast processes shaping their world, yet their evolution mirrored them. The creatures that live near the equator developed adaptations for dryness, thicker skin, better water retention, eggs that could survive outside of water. In the seas, new species of fish and invertebrates emerged to fill niches left by those that vanished. The planet's biological and geological histories moved together, each influencing the other, both parts of one continuous system. The slow embrace of stone was not just a meeting of land, but a merging of histories. Every continent carried billions of years of geological memory, ancient crust from earlier supercontinents, remnants of volcanic arcs, fragments of oceanic plates. When they joined, those stories fused. Rocks from different origins were pressed together, their minerals mingling, their layers overlapping. In a sense, Pangea was a library of the planet's past, its crust an archive of every collision that had come before. When we read those rocks today, we're reading the handwriting of time itself, folded, compressed and rewritten through heat and pressure. Over the course of millions of years, as the collisions continued, the outlines of Pangea became clear. From pole to pole, the land formed a single continuous surface. The supercontinent stretched across the equator, its coasts touching nearly every ocean current. The climate stabilised into a pattern of extremes, hot and dry in the interior, milder near the coasts, cold at the poles. Winds swept unbroken across thousands of kilometres. Rain clouds drifted from oceans to mountains, losing their moisture before they could reach the centre. Deserts expanded while coastal forests clung to the edges. It was a world of vast distances, connected yet divided by its own scale. Even as the continents finally locked together, the Earth did not rest. The same forces that had created Pangea would, in time, begin to pull it apart again. The mantle currents that drew the plates together would eventually shift direction. Cracks would form, stretching the crust in new ways. Magma would rise again, creating rifts that would one day become new oceans. The cycle would continue, as it always had, the planet endlessly balancing between creation and separation. But that part of the story still lay far in the future. For now the world was one, a single continent surrounded by a single ocean, alive with heat, pressure, and change. The slow embrace of stone was complete, though the Earth would keep reshaping the details for millions of years more. The mountains would grow higher, the deserts would spread, the rivers would deepen their paths, and through it all life would keep adapting, finding new ways to survive on a planet that never stopped moving. From the depths of the mantle to the edges of the sky, the Earth was always in motion, always folding, always breathing. The continents had met, the world had changed, and the story was still only beginning. By the time the last fragments of land met, the world had already been rearranging itself for tens of millions of years. The slow collisions that began in the late Carboniferous had finally drawn to a close, and the outlines of a new Earth were visible. Continents that had once drifted separately through warm seas now pressed together, locked in place by the immense weight of converging crust. The birth of Pangea was not a sudden event, not something that could ever be marked by a single moment or year. It was a gradual, unrelenting culmination of movement, a process so slow that mountains rose and eroded while the continents were still closing, the last of the gaps between them. What emerged from that long embrace was unlike anything the planet had known before. From near the North Pole to the far southern reaches of the world, a single, continuous landmass stretched across the globe. It was the largest supercontinent in Earth's history, its surface covering almost a third of the planet's area. Around it lay one vast ocean, the Panthalassa, whose waves touched every coast, circling the world in uninterrupted motion. To the east, a smaller sea called the Tethys formed in the space left by twisting fragments of crust, a narrow channel that would one day give rise to new continents. The planet had reached one of its most unified states, a world gathered together into a single face of stone. If you could have stood on the surface of Pangea then, the scale of it would have been beyond comprehension. The horizon would stretch endlessly, and the land beneath your feet would be part of an unbroken expanse that continued thousands of kilometers in every direction. The nearest ocean might lie farther away than any distance you could walk in a lifetime. Rain that fell on the coast might take months or years to reach the center of the continent, carried slowly by rivers that wound through plains and deserts too vast to cross. The climate of this new world was shaped by its sheer size. The edges were humid and green, while the interior grew dry, swept by winds that carried heat from day to night with little moisture to soften their path. The formation of Pangea changed everything: the atmosphere, the oceans, and the life that covered the land. When continents move, they don't just reshape geography, they alter the planet's balance of air and water. The closing of oceans disrupted the flow of currents that once carried heat around the world. The joining of land changed how winds formed and where clouds gathered. Rain no longer fell evenly across the Earth. The interior of Pangea received little moisture, becoming a land of extremes, while the coasts remained temperate and fertile. Deserts grew in the middle of the continent, stretching across regions that are now parts of modern Africa, North America, and Asia. The sands of those deserts still exist today, preserved in red rocks that tell of ancient dryness. The mountains that mark the seams of collision were immense. The Appalachians in what is now eastern North America stood young and rugged then, their peaks newly formed and still rising. The Urals in northern Eurasia extended like a long scar where two halves of the world had met. Across the southern hemisphere, ranges formed as Africa collided with South America and Antarctica. These mountains shaped weather patterns, redirecting winds and trapping clouds along their slopes. Rain fell heavily on one side and left the other dry. Rivers began their long journeys to the sea, carving valleys through the new highlands. The erosion of those mountains would, over millions of years, fill the lowlands with sediment, building fertile plains and basins that became homes to life. The atmosphere itself was different in those days. The great forests that once covered much of the Carboniferous world had declined as the continents came together. Oxygen levels, which had been unusually high, began to drop toward more familiar levels. The air grew drier and less dense, and the temperature patterns shifted with the changing geography. Seasons became more pronounced in many regions, with hotter summers and colder winters. Dust storms carried red silt across the interior plains, while coastal regions saw alternating periods of wet and dry as monsoon winds rose and fell. The joining of the continents had unified the land, but it also divided the climate, creating sharp contrast between one region and another. In the midst of these changes, life continued to adapt. The Permian world that followed was home to creatures both strange and familiar in form. On land, early reptiles and their relatives roamed the dry plains. Some grew large and heavily built, their bodies adapted for conserving water. Others stayed small and quick, moving through the sparse vegetation in search of insects and shelter. The synapsids, ancestors of mammals, began to diversify, developing new ways to regulate their body temperature and survive in the heat. Amphibians, once dominant in the swampy forests of the past, were now limited to wetter areas near rivers and lakes. The ecosystems of the interior were tough, resilient and sparse, shaped by drought and distance. In the ocean surrounding Pangea, life flourished under different conditions. The Panthalassa was vast beyond imagination, and its currents circulated slowly, carrying nutrients and heat around the globe. Along the continental margins, coral reefs and marine communities thrived in warm shallows. Ammonites and nautiloids floated through the open waters, while fish of many kinds filled the seas. The food chains of the oceans depended on the delicate balance of sunlight, currents, and temperature, a balance now influenced by the arrangement of the continents. Upwellings of nutrient-rich water supported blooms of plankton that fed entire ecosystems. Yet, even here, the great unification of land was leaving its mark. The single ocean meant fewer barriers between habitats, allowing species to spread widely, but it also made the planet more vulnerable to large-scale environmental changes. Geologically, the birth of Pangea was marked by intense activity. The mantle below continued to push and fold, adjusting to the new distribution of mass above. The weight of the continent depressed parts of the crust, creating basins that filled with water and sediment. The thickened crust of the mountain belts trapped heat, leading to episodes of metamorphism that transformed old rocks into new. Faults cut through the land, releasing pressure in occasional bursts that rippled across the ground as earthquakes. Volcanoes dotted the edges of the supercontinent, releasing ash and gas into the atmosphere. Though the process appeared calm from a cosmic distance, the Earth was restless beneath its surface, always adjusting, always finding equilibrium through motion. The centre of Pangea, cut off from the influence of the sea, developed into one of the most arid regions in the planet's history. The lack of nearby oceans meant that air masses lost their moisture long before reaching the interior. The result was a vast, dry expanse that stretched across what is now Central Asia and North Africa. There were few plants, only low shrubs and hardy conifers that could survive the long droughts. Winds swept across open plains, carving dunes and depositing red sands that would eventually harden into rock. Even in this harsh environment, life persisted. Small reptiles, burrowing animals, and insects that could withstand the heat. Fossil footprints found in these ancient desert deposits still trace the paths of those creatures, their delicate impressions preserved in time. Along the coasts, conditions were different. There, the proximity to the ocean created cycles of wet and dry, supporting forests of conifers and seed ferns. Rivers flowing from the mountains carried nutrients that enriched the soil, allowing more diverse plant life to grow. These areas became refuges for many species, places where water and vegetation provided shelter from the harsher interior. The boundaries between land and sea were dynamic, constantly shifting as sea levels rose and fell. Periods of global cooling caused the polar ice to expand, lowering sea levels and exposing new land. Warming phases melted the ice, flooding coastal plains and forming shallow seas that supported marine life. The Earth's climate, even under a single supercontinent, never settled completely. It moved in long, slow rhythms of change. The creation of Pangea also brought deep geological consequences that would unfold long after its formation. The subduction zones that had consumed the old ocean floors continued to operate, but now they were concentrated along fewer boundaries. Heat built up beneath the massive continent, trapped by its insulating crust. That heat would later help initiate the rifting that eventually tore Pangea apart, but for now it drove volcanic activity and mountain building. The supercontinent's size also affected the circulation of the planet's interior. slowing the rate of cooling within the mantle. The Earth had gathered itself into a single shell, and that unity came with strain, a balance between stillness and pressure that could never last forever. For the organisms living through these changes, the world was both connected and isolated. A reptile that evolved in one part of Pangea could, in theory, walk across the continent over generations, spreading its descendants across thousands of kilometres. There were no ocean barriers to stop migration, but in practice the harsh climates of the interior made such journeys rare. Populations became separated by deserts and mountain ranges instead of seas. Evolution followed new paths, shaped by the challenges of dryness and distance. Over time, distinct ecosystems formed despite the physical unity of the land. Forests in the coastal zones bore little resemblance to the barren plateaus inland. Life adapted not to the size of the world, but to the local rhythms of its corner. The joining of the continents also influenced the chemistry of the oceans. As rivers carried eroded material from the mountains into the sea, nutrients like phosphorus and iron entered the water, fueling biological productivity. This, in turn, affected oxygen levels in both sea and air. During certain intervals, oceanic circulation slowed, leading to low oxygen conditions in deeper waters. Layers of black shale from the Permian record these episodes, times when parts of the sea became stagnant, limiting the life that could survive there. These fluctuations foreshadowed larger environmental shifts still to come, changes that would eventually lead to the most severe extinction event in Earth's history. But during Pangea's birth, the balance still held. The world was stable, alive, and growing into its new shape. In many ways, the creation of Pangea marked a turning point in the evolution of the planet's systems. It represented both a peak of order and a beginning of instability. The continents had found each other, completing a cycle that had been turning for billions of years, yet in that unity lay the seeds of future division. The forces that brought the land together could not rest indefinitely. Heat and motion continued beneath the crust, preparing for another era of movement. But for a time, for millions of years, the Earth remained whole. In that age, the world's surface told a single story. From the frozen poles to the equatorial deserts, every mountain and plain was part of one continuous landscape. The creatures that lived there belonged to a planet with no true boundaries of land, only the vastness of the ocean that surrounded everything. The winds blew across the supercontinent as if the Earth had taken one long, deep breath. The rivers carved their paths in quiet persistence. The mountains stood young and restless, their peaks weathering under the same cycles of rain and sun that shape landscapes today. And beneath it all, the deep currents of the mantle continued to move, slow and steady, keeping the planet alive. The great joining was complete in form, though never in motion. Pangea had been born, not in a single instant, but through 1 billion small changes accumulating over time. The Earth had gathered itself into one vast body, a continent that stretched from horizon to horizon, wrapped in the same sky, surrounded by the same sea. Every rock, every grain of sand, every ripple of the ocean carried the signature of that union. It was a world both new and ancient, a balance of stability and tension that would define the planet for the next 50 million years. The land had finally come together, but the consequences of that unity were only beginning to unfold, shaping climates, species, and the course of life itself as the story of Pangea continued to evolve beneath the turning sun. The world had stopped drifting, at least for a while. The continents had come together, locking into a single vast shape that covered much of the planet's surface. For the first time in hundreds of millions of years, the land was one continuous mass, surrounded by the endless expanse of a single global ocean. But unity did not mean stillness. The Earth continued to breathe, slowly through the shifting of air, the movement of water, and the invisible motion of heat beneath the crust. The supercontinent was alive in its own way, and every part of it, mountain, plain, desert and shore, was connected by that deep planetary rhythm. The atmosphere that settled over Pangea was unlike any before it. The vastness of the continent created weather patterns that the planet had never experienced. Winds no longer had oceans to cross freely. They were forced to travel thousands of kilometres across open land, heating under the sun, losing their moisture as they went. By the time they reached the interior, they were dry and hot, stripping water from the soil and plants. The centre of Pangea became a land of extremes, scorching days, cold nights, and air so arid that clouds rarely formed. It was here that the great deserts of the Permian spread, covering much of what is now Central Asia, Northern Africa, and the southern parts of North America. The sand dunes that built up there left behind the red rocks we find today, a memory of the dryness that once dominated the heart of the supercontinent. Along the coasts, the world was different. There, the presence of the ocean softened the air, drawing moisture inland and creating seasonal rains. Monsoons swept across the shores, driven by the difference in temperature between land and sea. During the hot months, air rose from the continent's surface, pulling moist air in from the ocean. Torrential rains fell for weeks, flooding rivers and feeding forests that lined the coasts. When the seasons changed, the winds reversed, carrying dry air back toward the sea. These monsoon cycles became one of the defining features of Pangea's climate, regulating the rhythm of wet and dry growth and decay across its vast edges. In some regions, the yearly rains built thick soils and dense vegetation. In others, they brought only brief relief before the dryness returned. The global climate itself was complex and often unpredictable. The arrangement of a single supercontinent and a single superocean meant that air and water circulated on scales the planet had never known. Heat built up over the land, while the Panthalassa absorbed and redistributed it through slow, deep currents. The difference between land and sea temperatures drove winds that shaped global weather patterns. Near the equator, warm, moist air rose, feeding massive storm systems. At higher latitudes, cooler, drier air descended, creating belts of aridity that stretched across much of Pangea's interior. The balance of these forces shifted over time, producing cycles of climate that lasted thousands or even millions of years. There were periods when the earth warmed, when glaciers melted and the seas rose. There were others when the poles grew cold again, ice creeping across the southern regions of Gondwana. These shifts were influenced by changes in the planet's orbit, its tilt, and even the composition of the atmosphere. Volcanic eruptions along the seams of the supercontinent released gases into the air, including carbon dioxide, which trapped heat and altered global temperatures. Ash from eruptions could temporarily cool the planet by blocking sunlight, while the longer-term effects of greenhouse gases often reversed the trend, leading to warming. The climate of the Permian was a balance in motion, a reflection of the Earth's constant adjustments to its own internal and external forces. The air that filled the skies above Pangea was thinner and drier than that of the lush, carboniferous world that came before. The great swamp forests of that earlier age had drawn down carbon dioxide and produced abundant oxygen, but as those forests declined and new, drier ecosystems took their place, the chemical balance of the atmosphere shifted. Oxygen levels dropped to around 20%, close to what we breathe today, but far less than the 35% that once allowed giant insects to thrive. The reduction in oxygen affected both the size and metabolism of many species. Insects grew smaller, fires became less frequent, as the air could no longer feed them so easily. The atmosphere had found a new equilibrium, shaped by the vastness of the land and the changing patterns of life. The surface of the continent itself influenced the air above it. When the sun rose over Pangea's interior, the rock and soil absorbed heat quickly, warming the air and creating rising columns of wind that drove convection currents through the atmosphere. These movements drew cooler air from the coasts, reinforcing the monsoon cycles that defined the seasons. At night, the land cooled rapidly, and temperatures dropped by tens of degrees. The daily cycle of heating and cooling was far more intense in the interior than it had been when smaller continents were separated by ocean. The supercontinent amplified the contrast between day and night, wet and dry, heat and cold. It was a world of constant fluctuation, even in its long-term stability. In the lowlands near the coasts, rivers wound through broad valleys, carrying sediment from the mountains to the sea. Each flood season brought new layers of silt, building fertile plains that supported forests of conifers and seed ferns. These plants, with their deep roots and water-conserving leaves, were perfectly adapted to the new climate. They could survive both drought and flood, spreading across the continents wherever conditions allowed. Their presence stabilized the soil and created habitats for animals, forming the backbone of Pangea's terrestrial ecosystems. The air would have been filled with the scent of resin and dry earth, the sound of insects and small reptiles moving through the undergrowth. Farther inland, where rain rarely fell, vegetation grew sparse. The landscape was dominated by rocky plateaus and dunes of red sand. Occasional oases supported patches of life, small plants, insects, and hardy reptiles. These isolated ecosystems were like islands in a sea of dust, their survival dependent on the rare arrival of water from distant storms. The animals that lived there were masters of endurance. Early reptiles evolved scales that reduced water loss and eggs that could survive the dry air. They dug burrows to escape the heat and emerged at dusk to feed. Fossilized footprints preserved in ancient desert sandstones record their movements, tiny tracks that wind across the surface of the rock like signatures left by time itself. Even the ocean was affected by the birth of Pangea. The Panthalassa, though immense, was influenced by the position of the continents that surrounded it. Currents moved slowly across its surface, driven by the rotation of the planet and the distribution of heat. The Tethys Sea, wedged between the eastern edges of Pangea's landmasses, became a cradle for marine life. Warm and shallow, it hosted reefs built by sponges, algae, and early corals. Fish and ammonites swam in its waters, while plankton drifted in the sunlit layers near the surface. These ecosystems were rich and diverse, supporting species that would later spread across the oceans as the continents began to drift apart again. The deep ocean, however, was less hospitable. The vastness of the Panthalassa limited circulation in its depths, leading to areas where oxygen was scarce. Sediments deposited in those regions tell the story. Dark, organic, rich layers that formed when decaying matter sank into stagnant water. Life persisted mostly near the coasts and shallower seas, where sunlight and nutrients were available. Yet even in the deep ocean, certain organisms adapted to the darkness and low oxygen, evolving unique forms that would leave their traces in the fossil record. The ocean, like the land, was a world of contrasts, rich in some places, barren in others. The atmosphere above all this was not uniform. Dust from the deserts was carried high into the sky, spreading across the continent and even reaching the oceans. Volcanic eruptions injected aerosols into the air, changing how sunlight was scattered. These particles influenced weather and climate, sometimes cooling the surface temporarily, sometimes promoting rainfall when they acted as nuclei for cloud formation. Over long timescales, these effects balanced out, but in the short term, they added variety to the planet's weather. The supercontinent breathed in cycles of dust and rain, its climate a reflection of the interplay between rock, air, and life. The connection between the land and the atmosphere was constant. When plants spread, they altered the gases in the air, drawing down carbon dioxide and releasing oxygen. When the climate warmed and vegetation retreated, the opposite occurred. This feedback loop helped regulate the Earth's temperature, keeping it within a range suitable for life. The birth of Pangea intensified this interaction by concentrating so much land in one place. Weathering of rocks along mountain ranges absorbed carbon dioxide, cooling the climate over time. When volcanic activity increased, the released gases counteracted that effect, adding heat back into the system. The result was a dynamic balance, a slow oscillation between warm and cool phases that kept the planet's systems in motion. As millions of years passed, the ecosystems of Pangea became more established. Forests spread along river valleys and coastal regions. Deserts stabilized under wind-shaped dunes. Reptiles diversified, giving rise to new forms suited for the varying climates. Insects adapted to pollinate the early seed plants, forming ecological partnerships that would endure for hundreds of millions of years. The air carried the faint hum of life, even in the driest places. Everything moved according to the planet's rhythms: rainfall, wind, growth, decay. The supercontinent had its own weather, its own seasons, its own long breath that stretched across geological time. The Earth's magnetic field too recorded this era of unity. As lava cooled along the spreading centres of the ocean floor and as volcanic rock solidified on land, tiny magnetic minerals aligned with the direction of the planet's field. These minerals acted as compasses frozen in stone, preserving a record of where the continents had been. Today, when scientists study those magnetic patterns, they can trace the movement of the plates, reconstructing the shape of Pangea and the paths it took before and after its formation. The breath of the supercontinent was not only atmospheric, it was magnetic, geochemical, and deep. Every layer of the Earth responded to its presence. The climate systems of Pangea left their mark on the biosphere in subtle ways. Seasonal extremes encouraged migration and adaptation. Animals developed strategies to cope with scarcity, whether by hibernation, burrowing, or long-distance movement. Plants evolved seeds that could remain dormant through dry periods, waiting for the rains to return. Evolution became a dialogue between life and climate, each shaping the other over vast timescales. The creatures of the Permian were not yet the dinosaurs that would one day inherit the Earth, but their ancestors were already learning how to live in changing worlds. The supercontinent was a testing ground, a place where resilience was rewarded and specialization determined survival. The deserts that covered much of the interior were immense, but they were not lifeless. Scattered among the dunes were basins that occasionally filled with water after storms, creating temporary lakes. Around these lakes, algae bloomed, insects bred, and animals gathered. When the water evaporated, salt crystals formed, leaving behind white crusts that shimmered in the sunlight. Each rainfall began the cycle anew. These ephemeral lakes preserved fossils that tell us about the animals that lived there, footprints, bones, and impressions left in the drying mud. They show that life never truly retreated, even in the harshest conditions. The supercontinent, vast and dry as it was, still supported an intricate web of ecosystems linked by the flow of water and air. The breath of the supercontinent reached even into the rocks themselves. As mountains eroded, their sediments carried minerals that reacted with the atmosphere, capturing carbon and forming new compounds. These processes, though invisible, helped regulate the planet's chemistry. The weathering of silicate rocks drew carbon dioxide out of the air, while volcanic activity replenished it. The balance between these forces maintained the climate within a stable range over millions of years. The Earth was self-regulating, using its own geological and biological processes to maintain equilibrium. The formation of Pangea didn't disrupt that balance. It became part of it, another expression of the same deep feedback that had governed the planet since its beginning. To live on Pangea would have been to experience a world both immense and intimate. The horizon never ended, yet every storm, every wind, every shifting of the air was part of a single system. The same monsoon that soaked the forests of the coasts would, weeks later, fade into the dry winds of the interior. The same dust that lifted from the deserts would drift over the oceans, feeding plankton with its trace minerals. Everything was connected by circulation, by the slow exchange between sea, sky, and soil. The Earth's breath was global now, a unified motion that tied every corner of the planet together. And though the continents no longer moved much at the surface, the motion beneath never ceased. The mantle continued to flow, the heat of the earth rising and falling like the pulse of a hidden heart. The crust flexed under its own weight, creating new faults and small rifts. Over millions of years, that stored heat would begin to build pressure again, laying the groundwork for the next great change. But at this point in its story, the planet was steady. The supercontinent stood strong. The air above it shifted in vast looping patterns, carrying warmth and dust and life across the world. The Earth was breathing deeply, balance between creation and tension, waiting for whatever motion would come next. The land was whole, the air dry, the seas deep and wide, and in that stillness life carried on. The age of Pangea was not silent. It was filled with movement, slow, deliberate, purposeful. Creatures of every shape and scale inhabited the edges of the supercontinent, from the coasts washed by warm tides to the deserts that shimmered in the centre. It was a world that tested survival in ways the planet had never done before. To live on Pangea meant to endure heat and drought, to adapt to vast distances, and to find balance in an environment that could shift from generous to hostile in the span of a single season. The ecosystems that spread across this world were shaped by the extremes of climate. Along the coasts, where moisture from the ocean still reached the land, forests thrived. These were not the dense jungles of earlier ages, but landscapes of towering conifers, tree ferns, and seed-bearing plants. Their leaves were tough and waxy, built to resist evaporation under the strong sunlight. The forests spread along river valleys and deltas, places where water and silt built the foundations of complex food webs. Here, the air was warm and heavy, filled with the hum of insects and the soft movements of small reptiles among the roots. Amphibians lingered near ponds and streams, their lives still tied to the presence of water. The air carried the smell of resin, damp soil, and the faint mineral scent of the nearby sea. The creatures that lived among these forests were varied and resilient. The dominant vertebrates of the time were not dinosaurs yet, but their early relatives, the synapsids and the reptiles that would one day give rise to them. Among the synapsids were species that would eventually lead to mammals, though at this point they were reptile-like in appearance. Some, like Dimetrodon, carried tall sails of bone along their backs, likely used to regulate temperature. Others, smaller and more agile, hunted insects and small animals in the undergrowth. These creatures were warm-blooded or close to it, their metabolism more active than the reptiles that shared their world. They filled ecological niches that mammals would later inherit, their existence an early rehearsal for the future. In the shallower lakes and wetlands of the coasts, amphibians of remarkable variety still thrived. They were survivors from an older world, adapted to both water and land. Some grew large, with wide, flat heads, and bodies shaped for ambush. They lurked beneath the surface, waiting for smaller creatures to pass, snapping them up with quick strikes. Others were smaller and more agile, darting between patches of vegetation. Their skin needed moisture, so they remained close to water, living in the margins between ecosystems. Each rainy season renewed their world, flooding basins and filling temporary ponds where eggs could be laid. When the heat returned and the water dried, many perished, but enough survived in deeper pools to continue the cycle. The interior of Pangea offered far fewer comforts. As the land stretched inward, the climate grew harsher. The air was dry, the soil thin, and the rains rare. In this vastness, only the hardier species could survive. The plants here were low and sparse, tough shrubs, cycads, and scattered conifers clinging to the rocky ground. Their roots reached deep for water, and their leaves were small to conserve moisture. The animals that roamed this land were adapted to the same scarcity. Reptiles with thick, scaly skin moved slowly through the heat, conserving energy. Some burrowed to escape the midday sun, emerging only at dawn and dusk. Insects and small arthropods lived among the rocks, feeding on dry plant matter or each other. The desert ecosystem was simple but persistent, each species playing its role in the balance of limited life. There were rivers that cut through these dry lands, their courses changing over time as the ground shifted. These rivers were lifelines, narrow strips of green running through the red dust. Along their banks, more vegetation took hold, and life gathered there in abundance. Fossil evidence from these areas shows tracks of animals coming to drink. The impressions of claws and tails pressed into mud that would later harden into stone. Herds of reptiles followed these waterways, feeding on the plants that grew near them and laying eggs in the softer ground. Predators followed, their trails winding through the same channels. Every drought turned the rivers to cracked clay, and every rare flood brought new fertility. Life here was cyclical, patient, and perfectly tuned to the rhythm of scarcity. In the skies above Pangea, there were no birds yet, but insects ruled the air. Dragonflies with wingspans still impressive by modern standards hovered over water, their flight controlled and precise. Beetles, cockroaches, and early relatives of modern wasps and crickets filled the ecological roles of pollinators and decomposers. Their buzzing would have been one of the most constant sounds in the Permian landscape, a background hum of countless wings and legs. Many of these insects were smaller than their carboniferous ancestors, a result of lower oxygen levels, but their variety had increased. They fed on plants, pollen, carrion, and each other, forming a network of energy that connected every ecosystem from the coast to the desert. Out at sea, the story was equally rich. The Panthalassa was home to an astonishing diversity of marine life, though many lineages were already beginning to evolve into the forms that would dominate later periods. Coral reefs flourished in warm shallows, built by sponges, bryozoans, and early scleractinian corals. Fish of every shape swam among them, from small fast swimmers to larger predators with jaws lined in sharp teeth. Ammonites and nautiloids drifted through the open water, their spiral shells perfect for buoyancy. Crinoids waved their feathery arms from the seafloor, filtering nutrients from the currents. Sharks hunted across the continental shelves, some sleek and swift, others broad and flat, feeding near the sandy bottom. In the deeper ocean, life grew more mysterious. The vastness of the Panthalassa created regions of low oxygen, where few organisms could survive. These were places of still water, where organic matter accumulated and decayed slowly. Above them, plankton drifted in layers, forming the foundation of the food web. The interplay between sunlight, nutrients, and depth determined the richness of life in each region. Currents carried larvae and spores across immense distances, spreading life to every reachable corner. The ocean was as restless as the land, its inhabitants shaped by the same cycles of heat and change that moved through the atmosphere. The meeting of land and sea was where life flourished most intensely. Coastal environments, estuaries, deltas, lagoons were the transition zones that supported both marine and terrestrial species. Plants anchored the soil, stabilizing shorelines and providing food for insects and herbivores. Fish entered brackish waters to spawn, and amphibians hunted in the shallows. In these regions, the fossils show an overlap of worlds. Shells and scales, leaves and footprints, all preserved together. The edges of Pangea were places of convergence, where air, water, and stone met in dynamic balance. Farther inland, the diversity of life depended heavily on geography. The mountain ranges formed during the collisions that created Pangea acted as barriers and corridors. On their slopes, rain was more frequent, supporting forests and streams that sustained a different mix of species. In the rain shadows beyond, deserts spread. The variation in elevation created microclimates, small pockets of stability in an otherwise unpredictable environment. Within these pockets, species evolved in isolation, adapting to the unique conditions of their surroundings. Some of these lineages would vanish with time, others would endure, their descendants carrying traces of the Permian world into the ages that followed. The life of the Permian was also marked by competition and innovation. Reptiles diversified rapidly during this period, branching into forms that would dominate later ecosystems. The ancestors of turtles, lizards and crocodiles were already beginning to appear, though in primitive forms. Among the synapsids, some evolved specialized teeth and more advanced jaws, allowing them to process a wider variety of food. These small advantages accumulated over time, driving evolutionary change. Predators became faster, prey more cautious. Each adaptation triggered another, an endless exchange of advantage that kept life in motion. Beneath the surface, burrowing creatures shaped the land. Small reptiles, amphibians, and invertebrates dug tunnels in the soft sediments, creating networks that aerated the soil and mixed organic matter. These burrows provided shelter from heat and predators, serving as temporary refuges in harsh climates. Their fossilized remains give scientists a rare glimpse into the daily lives of animals that left no bones behind. The tunnels, often preserved in exquisite detail, show branching patterns and chambers where creatures rested or stored food. They reveal that life in the Permian was not confined to the surface. It extended downward into the cool earth, where the temperature was more stable and water could be found even in times of drought. Plant life during this era was undergoing its own transformation. The decline of the great swamp forest had made way for gymnosperms, plants that produce seeds instead of spores. These new plants were more resilient, capable of surviving in dry climates and poor soils. Conifers, cycads, and ginkgos spread across Pangea, forming forests in the wetter regions and sparse woodlands elsewhere. Their seeds could travel long distances, carried by wind or water, allowing them to colonize new areas quickly. Their roots stabilized the land, preventing erosion, and their fallen needles and cones enriched the soil. In this way, they shaped not only the ecosystems they inhabited, but also the physical landscape itself. The edge of the supercontinent was constantly changing. Sea levels rose and fell with shifts in temperature and ice accumulation at the poles. When the seas advanced, they flooded coastal plains, creating shallow inland seas rich in life. When they retreated, they left behind layers of sediment filled with fossils. These transgressions and regressions recorded the pulse of the earth, each cycle marking a new balance between land and water. The creatures that lived along these shifting boundaries had to adapt to constant change. Some developed life cycles tied to the rhythm of the tides, while others migrated inland or out to sea depending on the season. The edges of Pangea were never static. They were places of continual renewal. The air above this world was clear and dry, carrying dust from the interior across continents. Winds shaped dunes and eroded rock, but they also carried spores and pollen. These microscopic travellers spread plant life across vast distances, linking ecosystems that were separated by hundreds of kilometres. The global circulation of the atmosphere connected the forests of the coast to the deserts of the interior, the mountains to the plains. The same air that carried dust storms also carried the seeds of new growth. Even in the harshest environments, life found a way to expand its reach, using the planet's own breath as a vehicle. As the Permian Period continued, ecosystems grew more complex. Food webs expanded, and new species filled niches that had been empty before. The relationship between predator and prey evolved into intricate balance. The abundance of plant life along the coasts supported large herbivores, which in turn sustained predators. In the deserts, scarcity limited populations, keeping the system in equilibrium. Life adapted to both abundance and limitation, shaping itself around the patterns of the land. In every environment, survival was determined not just by strength, but by timing, by the ability to move, hide, or endure. The fossil record from this time reveals more than just bones and shells. It captures behaviour. Trackways show animals walking side by side, suggesting herds or family groups. Some footprints are preserved alongside the marks of tails and bellies, indicating the texture of the ground they moved across. The arrangement of bones in certain deposits hints at burrows or dens. These traces speak of lives lived in motion, of creatures navigating a landscape that was both immense and intimate. Each footprint, each imprint of a leaf or a ripple of sediment, is a frozen moment of Pangea's life. Even as the ecosystems of the supercontinent flourished, the forces beneath continued to shape their fate. The mantle's slow convection caused regions of the crust to rise and sink, altering sea levels and triggering episodes of volcanic activity. Eruptions released gases that affected the climate, at times causing warming or cooling that reshaped habitats. The Earth's systems were interconnected. No event occurred in isolation. The creatures of the Permian were part of a planet constantly in flux, adapting not just to geography but to chemistry and temperature as well. For millions of years this balance held. The supercontinent's edges supported lush forests and fertile plains. The interior remained a realm of deserts and sparse life. The oceans teemed with diversity, while the air above carried both dust and rain. It was a world of vastness and variation, united under one sky. Life persisted on every margin, every slope, every riverbank, finding a way to exist between abundance and emptiness. The edge of vastness was not a single place. It was the condition of the entire planet, a boundary between extremes where survival meant adaptation and endurance. And while the land appeared stable to any living thing that walked its surface, deep below, the planet's slow processes continued. Heat moved upward through the mantle, pressure built beneath the crust, and the same forces that had created Pangea were quietly preparing for what would come next. The life that thrived on the surface, unaware of those movements, was part of that story too. Each plant that drew carbon from the air, each animal that exhaled it again, each grain of sand carried by the wind, all were parts of the same breathing, the same global motion that defined the era. The world had reached its greatest scale, and on its surface life went on, adapting to the edge of vastness with quiet determination, shaping a planet that would soon begin to change once more. The forests that once covered Pangea's coasts and lowlands were changing. What had begun as an age of dense green canopies and swampy floodplains was slowly turning into a world of dryness and dust. The planet's breath had shifted again. The great rains that once fed vast rivers grew less frequent, and the steady warmth that had nourished so much life began to fluctuate. The air no longer carried the same moisture, and the balance that had allowed the forest to thrive started to fade. But even as the world grew harsher, the forests did not vanish all at once. They changed, adapting to the new rhythms of heat, fire, and scarcity that swept across the land. The trees that remained were survivors of older worlds. Conifers with thick bark and deep roots spread across regions that could still hold water. Their needles resisted evaporation, and their seeds were built to travel far, carried by wind to the next patch of soil capable of sustaining life. Cycads, with their sturdy trunks and crowns of stiff leaves, grew in clusters where groundwater lingered beneath the surface. Seed ferns clung to the edges of rivers and lakes, sending up new fronds each season in places where moisture still gathered. These plants became the backbone of the new forests, resilient, sparse, and built to endure long droughts. The cycle of fire began to shape these landscapes in ways the planet had not seen before. As the air dried and oxygen levels stabilized near modern values, wildfires became a regular part of the environment. Lightning strikes during dry seasons could ignite vast tracts of forest, sending flames racing through the undergrowth. The fires were fast, often consuming the surface vegetation and leaving behind charred trunks and layers of ash. But fire, destructive as it seemed, became a mechanism of renewal. The heat cleared away old growth, returned nutrients to the soil, and opened the cones of certain trees, allowing their seeds to scatter and take root. The forests of the Permian were not just living things, they were part of a continuous cycle of burning, decay, and rebirth. After each fire, the land changed colour. The blackened remains of trees stood briefly as monuments to what had been, and then wind and rain began to cover them with dust. The fine particles that filled the air after a blaze carried minerals that enriched the soil when they settled. In the months and years that followed, green returned, new shoots rising from the ash, mosses spreading across charred trunks, insects and small reptiles returning to hunt and hide among the recovering vegetation. The pattern repeated across regions, slow and steady, until the rhythm of fire became part of the life cycle of the forests themselves. The forests closer to the interior of Pangea faced a different challenge. There, the lack of rainfall meant fires burned hotter and lasted longer. When the trees died, they were not quickly replaced. Their remains fell and broke apart, the wood drying under the relentless sun. Winds carried away the lighter debris, leaving only fragments that mixed with sand and silt. Over time, these fragments became part of the red sedimentary layers that still mark the interior regions of the supercontinent. Those red rocks tell the story of a world that was not lush, but harsh. A world where forests struggled to hold on, and where dust became the dominant element of the landscape. Dust was everywhere. It coated leaves, filled the air, and drifted across entire continents. When the monsoon winds rose along the coasts, they lifted the fine grains and carried them inland, where they settled on rocks and valleys. Each grain was a fragment of erosion, particles from distant mountains ground down by rivers and carried by wind. The dust reflected sunlight during the day, cooling the surface slightly, but at night it trapped heat close to the ground. It was both shield and blanket, shaping the climate of Pangea in subtle ways. In the interior, it became part of the sky, a permanent haze that softened the horizon and gave the light a reddish tint. Even in the farthest forests, where water still flowed, the dust would settle on the needles of conifers, dulling their green. Insects adapted to the new conditions, their lives intertwined with the changing forests. Beetles and cockroaches thrived in the dry leaf litter, feeding on decaying wood and plant material. Termites evolved to break down the tough lignin in the bark and branches of conifers, becoming key decomposers in the ecosystem. Their tunnels aerated the soil, helping new plants take root. Pollinating insects continued their work, carrying pollen between plants that still relied on wind and movement rather than flowers. The interactions between insects and plants were growing more complex, setting the stage for future ecosystems where flowering plants would later dominate. For now, the Permian forests were defined by simplicity and endurance, each species focused on survival in a landscape that demanded it. The animals that roamed these forests moved in response to the changing seasons. Herbivores fed on the tough leaves of cycads and the soft shoots of young ferns. Some species developed specialized teeth for grinding the fibrous plant matter, while others relied on their size and endurance to travel long distances between sources of food. Carnivores followed them, hunting near water sources or waiting in the shade of sparse trees for the heat to ease. The smaller predators relied on stealth, blending with the bark and foliage, striking quickly before retreating into cover. Life in these forests required precision, every movement measured, every resource used carefully. The presence of fire shaped the behavior of animals as much as it did plants. When smoke rose on the horizon, creatures fled, moving toward rivers or open plains. Those that could burrow waited out the flames underground, sealed away from the heat. Afterward, when the fire had passed, they returned to a world transformed. The ash-covered ground was rich in minerals, attracting insects and the creatures that fed on them. The smell of smoke was a signal of both danger and renewal, a reminder of the fragile balance between destruction and life. Over time, many species learned to live with fire rather than against it, their instincts guided by the same patterns that governed the land. The forests also carried the memory of older worlds, the coal forests of the Carboniferous that had once stretched across low-lying swamps. Those lush, waterlogged ecosystems had been the lungs of the earlier Earth, drawing carbon from the air and storing it underground as layers of peat and coal. But by the time of Pangea, those swamps were gone, replaced by dry plains and uplands. The coal-forming plants had declined, unable to adapt to the new climate. What remained were forests that burned instead of drowned, releasing carbon into the air rather than burying it beneath the soil. The Earth's atmosphere responded accordingly, its composition shifting again. The balance between oxygen and carbon dioxide wavered, influencing temperature and rainfall. Fire was both a symptom and a cause, a reflection of the changing chemical exchange between life and air. In regions where volcanoes dotted the landscape, the connection between fire and life was even more direct. Eruptions scattered ash across hundreds of kilometres, covering forests and plains alike. The fine material preserved what it buried, sealing leaves, branches, and even footprints in perfect detail. These layers of volcanic ash, found in the rock record today, capture moments frozen in time, snapshots of forests before they burned, of rivers before they dried, of animals walking paths that would soon be buried. The volcanic activity added nutrients to the soil, stimulating regrowth once the eruptions ended. The same fire that destroyed life also sustained it, cycling minerals from deep within the earth back to the surface. The interplay of dust and fire created distinct patterns across the continent. Regions near mountains received more ash and fertile sediment, supporting thicker vegetation. The interiors, far from those sources, remained barren and dry. Wind carried the fine particles from one region to another, linking ecosystems through invisible exchange. The global circulation of dust even influenced the oceans. When it settled on the surface of the Panthalassa, it carried trace elements like iron, feeding plankton that formed the base of marine food webs. The cycle of erosion, transport, and deposition connected land and sea, showing that even in its dryness, the supercontinent nourished life beyond its own edges. The animals that depended on the forests faced an uncertain future. The shifting climate forced them to move constantly, following the retreating line of vegetation. Some species evolved to handle the changes, developing greater mobility, better heat tolerance, or more efficient ways to conserve water. Others vanished as their habitats disappeared. The fossil record shows alternating layers of abundance and scarcity, each corresponding to fluctuations in climate and vegetation. In some layers, fossils of herbivores are common. In others, they are absent, replaced by the remains of hardy desert dwellers. The pattern reflects the long breathing of the earth, a slow alternation between growth and decline that shaped every living thing on its surface. The red colour of the rocks from this time tells a story of oxidation, iron minerals exposed to air, reacting slowly over millions of years. It is the colour of dryness, of heat, of soil that rarely sees rain. It is the mark of an atmosphere that carried dust more often than clouds. When you see those red rocks today, whether in the American Southwest, Northern Africa, or parts of Europe and Asia, you are looking at pieces of Pangea's heart, the remains of its deserts and forests fused together by time. They are the silent witnesses of a world that burned, cooled, and breathed again, its surface constantly reshaped by the twin forces of fire and erosion. Despite the hardships, the forests endured. They moved with the land, their seeds spreading into new regions as old ones faded. In the wetter zones near the Tethys Sea, forests still reached impressive heights, shading rivers that wound through fertile plains. There, the humidity allowed for ecosystems more reminiscent of earlier ages, lush, green, and teeming with life. Amphibians and reptiles shared these habitats, and the air was thick with insects. Farther inland, however, each tree was a survivor, standing against wind and dust, its roots clutching at the dry soil. The sound of those forests was not a chorus of birds or rustling leaves, but the quieter, deeper rhythm of wind and the occasional crack of burning wood. The transition from green to red, from forest to desert, was not uniform. It happened in waves, depending on latitude, altitude, and local conditions. Some regions experienced temporary recoveries when monsoon rains returned for a few centuries, or when rivers changed their courses and brought new water. Others remained dry for millions of years. the planet's climate operated on scales far beyond the lives of the creatures that inhabited it. What seemed like an unending drought to one generation was merely a phase in the long cycle of the Earth's atmosphere and oceans. The forests of fire and dust were both transient and eternal, transient in their forms, eternal in their patterns. As Pangea continued to age, the processes that shaped it did not stop. The mantle below still pushed and shifted, creating new zones of uplift and subsidence. Volcanic activity continued along its margins, releasing gases that affected global temperatures. The carbon released by fires and eruptions fed into the atmosphere, altering the climate yet again. Each change triggered another, forming a chain of cause and effect that linked the land, air, and ocean. The forests responded as they always had, by adapting, burning, regrowing, and spreading. The dust continued to drift, carrying traces of the land into the sea, and the planet, in its slow, steady way, kept breathing through it all. There was beauty in this constant motion, though nothing about it was peaceful. The forests of the Permian were not gentle places. They were arenas of survival, shaped by forces far larger than the creatures that lived within them. Yet from that struggle came resilience. Every seed that took root, every tree that grew, every insect that fed and flew, was part of a long experiment in endurance. The fire cleared the way, the dust carried nutrients, and together they maintained the fragile balance that allowed life to continue. The forests of fire and dust were both the result of destruction and the source of renewal. They were the Earth's answer to change, its way of reminding itself that even in scarcity there is still growth, and even in burning there is still the promise of return. While the land of Pangea was dry and vast, its surrounding waters told a different story. The supercontinent may have gathered the planet's crust into one body, but in doing so, it left behind an ocean so immense it seemed endless. The Panthalassa stretched across nearly the entire surface of the Earth, a global sea that wrapped around the single mass of land like a living blue atmosphere. It was deep, restless, and filled with contrasts, hot shallows and cold depths, calm currents and violent storms, regions where life flourished in abundance and others where it struggled in near silence. The oceans of the Permian were extremes of heat and depth, of creation and decay, and within them the story of Pangea's life continued. The surface of Panthalassa was shaped by wind and temperature. The air that heated over the supercontinent rose and drew cooler air in from the sea, driving immense currents that circled the globe. These currents carried heat from the equator toward the poles and brought cold water back along the ocean floor. The result was a circulation system that connected every corner of the ocean. The temperature differences between regions were vast. Near the equator, the water shimmered under an unbroken sun, warm and rich with plankton. Farther toward the poles, ice formed at the edges of the sea, reflecting sunlight back into space. Between them stretched bands of transition, zones where life shifted from tropical abundance to polar simplicity. The ocean was alive with movement, an endless exchange of energy between surface and depth, heat and cold, air and water. The coasts of Pangea mark the border where these worlds met. Along the western edges, waves crashed against cliffs of new rock, eroding sediment into fine particles that fed the shallows. To the east, the Tethys Sea opened into a long warm gulf, surrounded by lowlands and reefs. These shallower regions were filled with life, thriving under steady sunlight and constant renewal. Coral-like organisms built reefs that stretched for kilometres, forming intricate structures where countless creatures lived. Fish darted among the corals, ammonites drifted in slow spirals above them, and crinoids waved their arms in the currents like underwater fields of grass. The reefs were the cities of the Permian Ocean, dense, active, and interdependent. Each organism relied on the waste, movement, and presence of others. The water was clear in those places, allowing light to penetrate deep enough to support photosynthesis. Algae and cyanobacteria formed the foundation of the food web, turning sunlight into energy and releasing oxygen into the water. Tiny plankton fed on them, and in turn they fed the larger species, small crustaceans, fish, and eventually the great marine predators. Sharks patrolled the reefs and continental shelves, their sleek bodies built for efficient hunting. Some grew large, capable of taking down anything smaller than themselves, while others specialized in hunting shellfish or scavenging along the seabed. The diversity of marine life during this period was remarkable, even though many species were beginning to evolve away from the forms of the earlier Paleozoic. The Permian Ocean was an ecosystem in transition, ancient lineages fading while new ones began to emerge. Beneath the surface, where sunlight no longer reached, the ocean changed character. The deep zones of the Panthalassa were cold, still, and often deprived of oxygen. The lack of strong circulation in some regions meant that water at the bottom could remain trapped for centuries or longer. In those depths, the decomposition of organic material consumed what little oxygen remained, creating vast anoxic zones where life struggled to exist. The sediments that formed there became dark layers of shale, rich in carbon and sulfur. These layers still appear in the geological record, marking the ancient stagnation of the deep sea. Yet even in these inhospitable regions, certain organisms found ways to survive. Bacteria capable of living without oxygen thrived in the sediments, feeding on sulfur compounds and producing new chemical energy that other microorganisms could use. Life had adapted to even the most extreme of oceanic conditions, turning scarcity into opportunity. Closer to the coasts, the seafloor was dynamic and full of life. Shellfish-like brachiopods and bivalves covered the sandy bottom, anchoring themselves in place or burrowing into the sediment. Trilobites, once among the most abundant marine animals on Earth, were fading into history, but a few species still lingered in specialized habitats. New groups of crustaceans and echinoderms took their place. Starfish and sea urchins grazed across rocks and coral, their movements slow but constant. Mollusks evolved new shells and forms, their spirals and ridges designed to withstand predation and waves. The seafloor was a mosaic of movement, every grain of sand turned over by something living. The Tethys Sea was smaller than the Panthalassa, but played an outsized role in the planet's ecology. Its warm, shallow waters connected tropical and subtropical environments, serving as a bridge between east and west. The currents that flowed through it carried nutrients and larvae, spreading species across thousands of kilometers. The reefs along its coasts acted as filters, capturing sediment from rivers and creating calm lagoons behind them. Those lagoons were nurseries for young fish and invertebrates, protected from open ocean predators. The Tethys also hosted vast beds of algae that formed dense mats near the surface. During the day, they photosynthesized and released oxygen. At night, they absorbed it again. This daily rhythm influenced the chemistry of the entire sea, a slow breathing that echoed the planet's larger cycles. The chemistry of the oceans was changing along with the land. The increased erosion from Pangea's young mountains sent minerals and nutrients into the sea, altering its balance of elements. Rivers carried calcium, iron and phosphorus into the coastal zones, feeding plankton and promoting the growth of reefs. But the same process also made the oceans more prone to periods of stagnation. When organic matter from these blooms sank into the deep ocean, it decomposed and consumed oxygen faster than circulation could replace it. This process, repeated over millennia, created conditions that could shift suddenly from abundance to scarcity. The Permian seas were rich, but they were also unstable, an intricate balance of productivity and depletion, always close to tipping one way or the other. Storms were frequent along the edges of the supercontinent. The temperature differences between land and sea created violent weather systems that churned the surface waters. Waves crashed with immense force against the coastal cliffs, reshaping them with each passing century. The spray carried salt and moisture inland, feeding narrow strips of vegetation that grew along the shore. These storms also played a role in ocean circulation, mixing surface layers and bringing nutrients up from the depths. After each storm, the water cleared and life resumed its cycle. The ocean's turbulence was not just destructive. It was a form of renewal, a reminder that energy and change were at the heart of Earth's stability. In the shallows, where sunlight and nutrients met, the variety of life continued to expand. Sponges filtered the water, forming the quiet foundation of many reef systems. Cephalopods, including early squid-like creatures, used jet propulsion to move quickly through the water, their intelligence already setting them apart from other animals. Some species developed hard shells, while others remained soft-bodied. Their speed and awareness their best defense. Among them swam fish with armor-like scales, and others with streamlined shapes that hint at the predators to come in later ages. Every movement, every adaptation was a response to the same set of pressures: the need to eat, to avoid being eaten, and to reproduce before the ocean took them back. The Panthalassa's scale made it both nurturing and isolating. The distances were so great that species on one side of the ocean could evolve independently from those on the other. The reefs near the equator bore little resemblance to the cold, sparse ecosystems near the poles, yet everything was connected by the slow flow of water and heat. Nutrients released by decaying organisms in one region might centuries later nourish plankton halfway around the world. The entire system was a vast conveyor of energy, powered by the heat of the sun and the rotation of the planet. Even in its most tranquil moments, the ocean was never truly still. When the tides receded along the coasts of Pangea, they left behind traces of that motion. Mudflats formed where the water lingered, filled with tracks of animals that moved between land and sea. Crabs, worms, and small fish left their imprints, preserved as ripples of activity in the sediment. Over time, these tracks were buried and turned to stone, recording a moment of life in transition. The boundary between ocean and continent was always shifting, yet the rhythm of the tides was constant. It was the heartbeat of the planet, marking the passage of time more faithfully than any clock. The chemistry of seawater during the Permian was also distinct from earlier ages. The concentrations of calcium and magnesium influenced the types of shells and skeletons that organisms could form. As the ratio between these elements shifted, some coral species declined while others flourished. Evaporation in the hot enclosed basins near the equator sometimes caused salt to crystallize out of the water, forming thick layers of evaporates that would later become sources of minerals and energy. These salt flats and shallow seas recorded the interaction between climate and ocean, a constant dialogue between evaporation, rainfall, and the movement of tectonic plates. Far from the coasts, in the open ocean, the sense of vastness was total. The horizon was unbroken, and the water stretched in all directions without a hint of land. The sun warmed the surface during the day, while at night the temperature dropped sharply. In the absence of continents to moderate it, the ocean experienced wide fluctuations between surface heat and deep cold. The creatures that lived in this expanse were adapted to solitude and endurance. Many were migratory, travelling thousands of kilometres to follow currents or spawning grounds. Others lived in the twilight zone, where light faded but life still persisted. Bioluminescent organisms illuminated the dark with faint glows, signalling to mates or confusing predators. Their light was the only constant in the blackness, a quiet affirmation that even in isolation life continued. The presence of a single, massive ocean affected not only climate but also the distribution of storms and seasons. The Panthalassa's ability to store heat meant that it moderated the planet's overall temperature, absorbing excess warmth during hot periods and releasing it slowly during cooler ones. However, this also made weather patterns more extreme in certain regions. The size of the ocean allowed storms to gather immense power before reaching the coasts. Waves several stories high could batter the shorelines, carrying marine debris far inland. Each storm reshaped the edge of the continent, eroding cliffs, depositing sediments, and leaving behind layers that told of their passing. The interaction between land and sea influenced evolution on both sides. Along the coast, species adapted to fluctuating salinity and water levels. Some amphibians began spending more time on land, taking advantage of new environments opened by the retreating tides. Fish developed stronger fins and lungs capable of absorbing oxygen from the air, precursors to future terrestrial lineages. These gradual changes built the foundation for the later expansion of vertebrate life on land. The ocean, though it seemed separate, was the source of every lineage that would one day walk the continents. The ocean floor beneath Panthalassa was also changing, though far too slowly to see. New crust formed along mid-ocean ridges, where magma rose from the mantle and cooled, pushing older crust outward. On the far sides, the old crust was subducted back into the earth at deep trenches, recycling the ocean floor. This process, imperceptible to any creature living above, maintained the planet's internal balance. It was the deep mechanism that allowed continents to drift, mountains to rise, and oceans to form. The surface life depended on this hidden motion, even if it would never sense it. At the edges of the supercontinent, the ocean's influence extended inland through humidity and rainfall. The monsoon systems, driven by the difference between land and sea, shaped entire ecosystems. In wet years, rivers swelled and carried sediments filled with organic material to the coast, feeding the marine food webs. In dry years, dust storms carried particles in the opposite direction, depositing them into the ocean. The exchange was constant, the flow of matter and energy moving in both directions. It was the planet's slow conversation with itself, the dialogue between stone and salt, air and water. The oceans of the Permian were places of abundance and danger. They supported a richness of life unmatched by most earlier eras, yet they were always near the edge of instability. The balance between oxygen and carbon, between temperature and circulation, was delicate. A small shift in one could trigger changes in the other. The same geological forces that had built Pangea were still at work beneath the sea, subtly altering the chemistry of the water through volcanic activity and seafloor spreading. These gradual shifts accumulated over time, setting the stage for future upheavals that no creature could foresee. For now, though, the oceans remained alive and dynamic, vast beyond comprehension, carrying the planet's energy from one end of the world to the other. Every wave that touched the shore was connected to another halfway around the globe. Every current that rose from the depths carried the memory of warmth from distant latitudes. The Panthalassa was not just a body of water, it was the planet's circulatory system, its constant motion the pulse of Earth itself. And along its margins, where the sea met the land of Pangea, life thrived on that pulse, building, dying, and beginning again under the same endless horizon. Beneath the calm surface of the Earth, long before any creature could have imagined such forces, the real motion never stopped. The continents of Pangea, wide and seemingly immovable, rested on something far less solid than stone. The crust that held mountains, deserts, and seas was only a thin shell over a deeper world of heat and slow motion. Down there in the mantle, matter flowed in currents that rose and sank like the invisible tide of the planet itself. Every movement of the surface, every shift in climate, every mountain that rose or sea that opened was the surface expression of that deeper pulse. The Earth's history has always been written not only in its rocks, but in the heat that drives them to move. When the continents came together to form Pangea, the internal balance of the planet changed. The crust beneath the supercontinent thickened as the edges of plates collided and folded. Mountains formed, subduction zones deepened, and the mantle beneath those regions began to respond. Where the crust pressed downward, the underlying material grew hotter under pressure, expanding and creating zones of buoyant uplift elsewhere. The Earth's mantle behaves not like a liquid, but like a slow-moving solid, flowing under immense pressure. Its motion is powered by heat, partly left over from the planet's formation, and partly from the decay of radioactive elements scattered throughout the interior. This constant release of energy drives convection, where hotter material rises, cools, and then sinks again, forming cycles that can last tens or hundreds of millions of years. Above this slow engine, the crust drifts in fragments. Each fragment, called a plate, carries continents, ocean floors, and mountain belts with it. Where plates move apart, new crust forms from molten rock that rises to fill the gap. Where they collide, one is pushed beneath the other, melting back into the mantle. This continuous recycling maintains the planet's structure. Nothing on Earth is truly fixed. It all moves at the scale of the mantle's rhythm. Even the most ancient rocks at the surface have travelled through cycles of uplift and burial, creation and destruction. Pangea was one of the temporary configurations in that ongoing sequence, a moment when the plates converged before they would inevitably drift apart again. The heat that powers these movements comes from multiple sources. Much of it is primordial, left from the time when the planet first formed from colliding debris more than 4 billion years ago. That impact energy was trapped inside, slowly leaking outward ever since. The rest comes from radioactive decay, atoms of uranium, thorium and potassium breaking down and releasing small amounts of heat over immense timescales. Together, these sources generate enough energy to keep the mantle soft and mobile. The outer crust cools and hardens, but the layers beneath it remain dynamic. The contrast between the cold, brittle surface and the hot, flexible interior creates tension, cracks and movement. The planet is constantly trying to balance its own temperature by transferring heat outward, and that motion is what drives the drifting of continents, the opening of oceans, and the eruption of volcanoes. Under Pangea, this process took on new intensity. The sheer size of the supercontinent acted like a lid, trapping heat within the mantle below. Normally, when continents are scattered, heat escapes more easily through the thinner crust of the ocean floors that separate them. But when the land is gathered into one mass, the thick continental crust acts as insulation. Over millions of years, the temperature beneath Pangea began to rise. The mantle under its centre grew hotter and more buoyant, while cooler, denser regions developed around the edges where subduction zones pulled old crust downward. This uneven distribution of heat created stress throughout the supercontinent. The surface appeared still, but deep below pressure was building. Volcanic activity along the margins of Pangea reflected this hidden energy. Subduction zones formed where the oceanic plates of the Panthalassa and the Tethys Sea descended beneath the continental edges. As they sank, the rocks released water and other volatiles, lowering the melting point of the surrounding mantle and generating magma. This magma rose toward the surface, creating arcs of volcanoes that lined the borders of the supercontinent. Each eruption released heat, gases and minerals into the atmosphere and oceans. The gases, mainly carbon dioxide, sulfur dioxide and water vapour, affected global temperatures and chemical cycles. Over time, volcanic activity played a major role in regulating Earth's climate, balancing the cooling effects of weathering and ocean absorption with new inputs of greenhouse gases. Inland, far from the active margins, the effects of the mantle's pulse were less visible, but no less important. The build-up of heat beneath the centre of Pangea began to cause gentle uplift, raising broad plateaus and thinning the crust in certain regions. Faults formed, invisible at first, marking the zones where the land would eventually begin to stretch and crack. These rifts would not open for millions of years, but the process had already begun. The planet was preparing, slowly and without urgency, for the next phase of its tectonic cycle. Even as Pangea reached its full form, the mechanism of its fragmentation was already underway beneath it. Earthquakes were another sign of this deep activity. Along the boundaries of Pangea's plates, where compression and subduction occurred, stress built up in the rocks. When that stress exceeded the strength of the crust, it was released as seismic waves that shook the land. These events, though brief compared to geological time, were part of the planet's constant adjustment to its own forces. The vibrations travelled through the Earth's interior, revealing its layered structure: crust, mantle, and core. Long after those ancient quakes ended, their traces remained in the deformed rocks and fault zones that record the planet's attempt to stay balanced while in motion. The heat moving upward from the mantle also influenced the chemistry of the oceans. At mid-ocean ridges where new crust was forming, hydrothermal vents released mineral-rich fluids into the seawater. These vents, driven by the same convective heat that moved the plates, created ecosystems entirely independent of sunlight. Microbes living near the vents used chemical energy from sulfur and methane to sustain themselves, forming the base of unique communities of tubeworms, crustaceans, and other organisms adapted to the darkness. These deep-sea environments were reminders that life on Earth was not confined to the surface. It thrived even in the most extreme conditions, sustained by the same internal heat that moved continents above. Over geological time, the balance between heat generation and heat loss has determined the pace of tectonic activity. Early in Earth's history, when radioactive decay was more intense, the mantle was hotter and convection faster. Continents moved quickly, colliding and breaking apart in shorter cycles. As the planet aged and cooled, the rate of movement slowed. By the time of Pangea, the mantle's heat output was lower than in the past, but still sufficient to drive large-scale motion. The formation of the supercontinent was both a result of that long cooling and a contributor to its continuation, as the insulating crust trapped warmth below. The Earth's pulse had slowed, but it was steady, deep, and enduring. The mantle's flow is difficult to imagine because of its timescale. It moves at speeds measured in centimetres per year, slower than the growth of a fingernail, but over millions of years, that small motion builds mountains, opens oceans, and rearranges continents. The rock within it behaves like a very thick fluid, creeping upward where it is warm and sinking where it cools. These slow currents carry enormous amounts of heat and material, mixing the planet's interior and renewing its surface. The top of this system, the tectonic plates, ride on it like rafts on a sluggish, invisible sea. Every volcano, every earthquake, every mountain range is an expression of that hidden motion. It is the physical heartbeat of the planet, a rhythm that has continued without pause for over 4 billion years. The core, far below the mantle, adds to this motion through its own heat and magnetic field. The outer core is molten iron and nickel swirling in convection currents that generate Earth's magnetic field. That field extends into space, protecting the planet from solar radiation and guiding the compasses of migrating animals. The movement of the core influences the mantle above, and vice versa. The two layers interact in ways we still struggle to understand, but together they form a single dynamic system. The energy released from the core helps maintain the convection in the mantle, and the mantle, in turn, controls how quickly the core cools. The pulse beneath the continents is therefore not isolated. It is part of a whole planet's circulation of energy and matter. During the time of Pangea, the magnetic field left its signature in the rocks that cooled from lava or sediments containing magnetic minerals. As these materials solidified, the tiny grains within them aligned with the direction of the magnetic field at that moment. Over millions of years, as continents drifted and the poles shifted, these records accumulated. Today, scientists can read them to trace the paths of the continents and the changes in Earth's magnetic polarity. The patterns show not only where Pangea once lay, but how it slowly began to move apart again. The rocks preserve the memory of the planet's invisible pulse, each layer a frozen record of direction and motion. The rising heat beneath Pangea affected not only the solid Earth, but also its surface conditions. Regions of elevated geothermal activity caused local volcanism, hot springs, and the release of gases that altered the atmosphere. In some areas, these emissions included methane and carbon dioxide, contributing to gradual warming. Elsewhere, large basaltic eruptions spread layers of lava across the land, forming vast plateaus. Each eruption released minerals that would later enrich soils and sediments. Even destruction led to renewal. The link between the planet's interior and its biosphere was constant. Heat and gases from below feeding chemical cycles above, setting limits and opportunities for life. As the Permian Period continued, the build-up of heat beneath the supercontinent became increasingly important. Over tens of millions of years, this trapped energy would eventually begin to fracture Pangea, opening rift valleys that would become the seeds of new oceans. The process was already underway in subtle ways: minor faulting, volcanic activity, and the gentle stretching of the crust. These early rifts were invisible to the animals and plants that lived on the surface, but in geological terms they marked the beginning of change. The Earth was preparing its next act, continuing its cycle of assembly and breakup, creation and destruction. The pulse beneath never paused. It only shifted focus. On shorter timescales, the planet's internal heat influenced weather and climate through volcanic outgassing and the release of aerosols. When large eruptions occurred, they injected sulfur compounds into the stratosphere, reflecting sunlight and temporarily cooling the surface. Afterward, as carbon dioxide accumulated, the climate warmed again. These fluctuations were small compared to the long-term patterns, but they shaped local environments and affected the evolution of species. Each eruption, each tectonic event, was part of the same slow dialogue between the deep earth and its surface, between fire and air, between motion and stillness. Even today, long after Pangea's fragments have drifted to new positions, the effects of that ancient pulse remain visible. The mountain ranges that formed during its assembly still stand, worn and eroded but unmistakable. The volcanic rocks that mark its boundaries record the flow of magma that once connected continents. The magnetic signatures in the seafloor reflect the spreading that followed its breakup. The Earth's history is a record of continuous movement, each era leaving its imprint on the next. The pulse that once built Pangea still beats beneath us, as steady now as it was then, reshaping the planet grain by grain, centimetre by centimetre. To imagine that motion is to picture the Earth as a living system. The continents are its crust, the mantle its muscles, the core its heart. Heat moves through it like blood, circulating, carrying energy, maintaining balance. The surface may seem calm, but beneath, the currents never rest. Pangea was only one phase in this circulation, one breath in a long sequence of expansion and contraction. The pulse beneath shaped its birth, sustained its existence, and would eventually drive its end. The continents drift, the oceans open and close, the mountains rise and erode, and through it all the same deep heat continues to move, unseen but eternal, powering the slow transformation of a planet that never truly stops. The world above the mantle's slow motion had settled into its own balance, a vast and changing experiment in air and temperature, in rain and drought, in wind that circled endlessly around the single landmass of Pangea. The climate of that time was not a single condition. It was a shifting system of contrast that covered every latitude and evolved through millions of years. The heat of the sun, the movement of the oceans, and the breath of volcanoes all worked together to create patterns that no living thing could control but every living thing depended on. The Permian climate was Earth's experiment in extremes, a combination of unification and division, where one world's geography created 1,000 different environments. When the continents had been scattered, oceans had softened the climate. Sea breezes carried moisture inland, storms spread rain across the land, and the air moved easily between hot and cold zones. But Pangea changed that. With so much land gathered into one body, the interior of the supercontinent was cut off from the moderating influence of the sea. air that rose moist from the ocean dropped its water along the coasts and reached the interior dry. The result was a vast expanse of arid land, an area so large that it developed its own weather systems. The centre of Pangea became a desert the size of continents, red and endless, while its edges supported forests and rivers that lived and died by the rhythm of the monsoon. The planet's circulation changed with this new configuration. Winds rose from the hot surface of the land, pulling moist air in from the Panthalassa and the Tethys Sea. As that air moved inland, it lost its moisture, releasing it as rain before crossing the mountain ranges near the coasts. What remained was dry, descending air that warmed as it sank, creating high-pressure systems that locked the deserts in place. The same process repeated across latitudes, producing alternating bands of climate, humid tropics near the equator, arid zones further inland, temperate forests at higher latitudes, and ice at the poles. The movement of heat between these zones set the pattern for global weather, one that would define the rest of the Permian. The temperature differences between day and night in the interior were extreme. Without the ocean's thermal buffer, the land heated quickly under the sun and cooled just as fast after dark. At midday, the surface baked under intense solar radiation, the air shimmering with heat. At night, the temperature could drop sharply, and dew formed only in the most humid places. Plants adapted to conserve water, developing tough leaves, deep roots, and thick bark. Animals learned to move with the temperature, resting through the hottest hours and emerging at dawn or dusk. Life became synchronized with the climate's rhythm, shaped by the contrast between light and darkness, heat and chill. Along the coast, the story was different. There, the proximity to the ocean softened the extremes. Seasonal winds carried moisture inland, feeding rivers and forests that supported diverse ecosystems. The monsoons of the Permian were immense, driven by the difference in temperature between land and sea. In the warm season, air over the supercontinent rose, drawing moist winds from the ocean. Rain fell for months, swelling rivers and filling lowlands with temporary lakes. When the seasons changed, the pattern reversed, bringing dry air and cooler temperatures. These alternating cycles defined the lives of countless species, determining when plants grew, when animals migrated, and when entire ecosystems flourished or faded. The chemical composition of the atmosphere played a key role in this balance. The levels of carbon dioxide were higher than today, partly due to volcanic outgassing from the tectonic activity that continued along Pangea's margins. This greenhouse gas trapped heat in the lower atmosphere, maintaining warm global temperatures even when parts of the planet cooled temporarily. The warmth allowed tropical conditions to extend far from the equator, supporting life in regions that would otherwise have been frozen. Yet the same mechanism also made the climate sensitive to small changes. When volcanic activity increased, releasing more carbon dioxide, temperatures rose. When weathering of rocks drew carbon dioxide out of the air, temperatures dropped. The Earth's climate was a dynamic balance between the sources and sinks of greenhouse gases, a system that could swing between stability and disruption, depending on how those forces interacted. During the early Permian, remnants of the last great ice age still lingered in the southern regions of Gondwana. Glaciers covered parts of what are now South Africa, India, and Antarctica. The ice sheets left behind striations in the rocks, scratches and grooves carved by their slow movement. As the climate warmed, the ice retreated, leaving behind valleys and basins that filled with rivers and lakes. The melting of this ice released fresh water into the oceans, slightly altering their salinity and affecting currents. Over time, the global climate shifted toward warmth, and the ice age ended. The polar regions remained cool, but the rest of the planet entered a long, warm phase that would last until the final, catastrophic events of the late Permian. The balance between hot and cold regions was not static. Periods of volcanic activity, orbital changes and shifts in ocean circulation periodically altered global conditions. When eruptions released large amounts of sulfur dioxide, sunlight was temporarily blocked, cooling the surface. When those effects faded, the carbon dioxide they emitted caused long-term warming. The Earth's orbit around the Sun also changed slightly over tens of thousands of years, altering the amount of sunlight reaching different latitudes. These cycles influenced rainfall, vegetation, and the distribution of ecosystems. The planet's climate was not a steady state, but a slow, perpetual oscillation. Each fluctuation shaped life in subtle ways, driving adaptations, migration, and extinction. One of the most striking features of the Permian atmosphere was its oxygen level. Earlier in Earth's history, during the Carboniferous, oxygen had been unusually high, supporting enormous insect and vast coal-forming forests. But as those forests declined and wildfires became more common, oxygen levels dropped to near modern values. This change affected everything from respiration to combustion. Fires burned differently, spreading slower and cooler than before. Animals with efficient lungs or higher metabolic control had an advantage, while others struggled in the thinner air. The atmosphere's new balance reflected the planet's adjustment to its changing biosphere. Every breath taken by a creature on Pangea carried within it the history of photosynthesis, fire and decay that had shaped the world's air. The seas surrounding Pangea mirrored these atmospheric patterns. Warm currents moved along the equator carrying heat toward the poles, while colder currents flowed back beneath the surface. This global circulation redistributed energy and influenced weather on land. When warm water met cold air, it produced massive storms that swept across the coasts, bringing rain and wind. The interaction between ocean and atmosphere was the engine of the planet's climate system, and its variations determined how habitable each region would be. Over millions of years, this balance shifted repeatedly, recording its rhythm in layers of sediment, evaporate, and fossilized soil. The climate also left its mark on the rocks. In some regions, alternating layers of sandstone and mudstone record cycles of wet and dry conditions. The coarser layers formed when rivers flooded their banks, carrying sand across the plains. The finer layers settled during calmer periods, when the waters receded and dust blew in from the deserts. These patterns repeat across vast stretches of Pangea's fossil record, a visual archive of the climate's long experiment. Each layer is a memory of a season that lasted tens of thousands of years, the product of the same wind and rain that shaped the surface of the land. Vegetation responded to these patterns by evolving new strategies for survival. Plants that had once relied on abundant moisture now adapted to aridity. The gymnosperms, with their tough seeds and waxy leaves, replaced the older spore-bearing plants of the Carboniferous. Conifers spread across highlands and dry plains, their needle-like leaves conserving water. Cycads and ginkgos grew in the more temperate regions, while seed ferns persisted in wetter areas near rivers and lakes. These plants played a crucial role in stabilizing the soil and regulating the atmosphere, capturing carbon through photosynthesis and releasing oxygen back into the air. In doing so, they helped maintain the balance that made life possible, even as the planet's surface grew harsher. Animals followed the vegetation. Herbivorous reptiles grazed on the conifers and cycads, while carnivores hunted them across the open plains. In the drier interior, creatures evolved to conserve water and survive heat. Some developed burrowing habits, escaping the temperature extremes by living underground. Others grew thicker skin or lighter coloration to reflect sunlight. Near the coasts, amphibians and aquatic reptiles took advantage of the wetter conditions, feeding on fish and insects. The diversity of life reflected the diversity of the climate, each region, each habitat, shaped by a combination of geography, wind, and heat. The interaction between land, ocean, and air made Pangea's climate unusually sensitive to feedback. When deserts expanded, they reflected more sunlight, cooling the surface slightly. When vegetation spread, it darkened the land and absorbed more heat, promoting rainfall. These effects balanced each other, but they also made the system prone to sudden shifts. A small change in temperature or volcanic activity could alter rainfall patterns across thousands of kilometers. The Earth's climate was like a network of interconnected levers, each responding to the others with a delay that stretched over millennia. In the far southern regions, the remnants of glacial cold still shaped the environment. Antarctica, joined to the southern edge of Pangea, was covered by ice caps that advanced and retreated with the seasons. The glaciers carved valleys and fjords, grinding rocks into fine sediment that rivers carried northward. When the ice melted, it released torrents of water that reshaped the land and deposited layers of silt in the oceans. These periodic meltwaters influenced sea levels, causing them to rise and fall over millions of years. The rhythm of the ice was slow but relentless, another part of the planet's experiment in temperature and flow. Volcanic gases played a subtle but significant role in this balance. The sulfur and carbon released from eruptions entered the atmosphere, where they interacted with water vapor and sunlight. Some formed aerosols that reflected solar radiation, while others contributed to long-term warming. The timing and scale of these emissions could determine whether a region cooled or heated, whether forests spread or shrank. Over geological time, these cycles built and dismantled ecosystems, their effects recorded in fossilized soils and isotopic signatures. The climate of the Permian was therefore not a single condition but an evolving system shaped by every eruption, every mountain uplift and every storm that crossed the sky. Even the colour of the rocks from that time tells the story of the atmosphere. The widespread red beds, sandstones and siltstones stained with iron oxides, formed in arid conditions under an oxygen-rich sky. Their hue is the product of oxidation, of minerals reacting with the air over long exposure. These rocks stretch across continents today, found in North America, Europe, Asia and Africa, remnants of the same supercontinent. They show that the dry, hot interior of Pangea was not limited to one region, but extended across much of the globe. The red earth of the Permian was the visual signature of its climate, a world where heat, dust and oxygen met under an unbroken sun. Through all this, life endured. The climate tested the resilience of every species, favouring adaptability over abundance. Those that could adjust to dryness, heat and variation survived. Those that required stability dwindled. Evolution proceeded quietly but efficiently, producing forms that could withstand scarcity and unpredictability. These were the survivors that would face the even greater challenges to come, when the planet's balance would falter under the strain of its own systems. But for now, the experiment continued. A world of warmth and dust, of monsoon and desert, of oxygen and fire. Every element of the climate was connected to the others, each one feeding back into the global system. The erosion of mountains drew carbon from the air. The growth of plants returned it in organic form. The movement of oceans distributed heat, and the movement of continents changed the paths of wind. The entire planet was an engine of feedback loops, adjusting constantly to maintain equilibrium. It was an experiment without design, without direction, only the natural outcome of physics, chemistry, and time. And through that process, the Earth found ways to balance its extremes, keeping itself within the narrow band of conditions that allowed life to persist. The climate of the Permian was neither entirely hostile nor entirely kind. It was a mixture of both, a demonstration of what happens when the planet gathers its continents into one and lets heat and air find their own order. Every storm, every drought, every shift in temperature was part of that process. From the frozen poles to the red deserts and green coasts, the world was learning the limits of its stability, testing how far it could stretch before balance broke. The grand experiment continued quietly under the same sun that shines today, and the results of that long trial were still unfolding across the face of the Earth. The world had found its pattern. Heat rose from the surface of the land, winds crossed the great continent, rains fell on the coasts and vanished before they could reach the interior. Life adjusted to that rhythm, as it always had, learning the new tempo of survival that the Permian world demanded. Nothing about this age was easy. The conditions that covered Pangea were severe, and yet the planet remained full of life. Every environment, from the driest desert to the shallowest sea, was occupied by something that had learned how to endure. The story of the time was not one of expansion but of persistence, of creatures and plants discovering how to adapt to scarcity and change without losing their place in the world. Across the lowlands and coastal plains, forests still stood. They were different from the lush swamps of the Carboniferous, but they supported a new kind of stability. Conifers, cycads, and seed ferns dominated the landscape. Their roots anchored the soil and trapped moisture, their leaves narrow and waxy to reduce water loss. They had become the foundation of life on land. The air within these forests was dry and warm, but not barren. Insects moved constantly, pollinating, feeding, decomposing. Reptiles climbed through the trunks or hid among the shadows of the roots. The trees themselves had evolved to resist both fire and drought, with bark that could survive high temperatures and seeds that could germinate after long periods of dormancy. These adaptations were not just responses to the environment, they were part of it, shaping how the ecosystem recycled nutrients and how fire moved across the land. The creatures that lived among those trees were part of a new order. The amphibians that had once dominated the Carboniferous were now limited to wetter regions, where streams and ponds provided the water their skins required. Their large, flattened heads and heavy bodies were relics of a wetter past. In their place, reptiles of all kinds had spread across Pangea. They were the first true masters of the land, able to live and reproduce without returning to water. Their eggs, encased in tough shells, protected developing embryos from drying out. Their skin, covered in scales, kept moisture inside. These adaptations freed them from the old boundaries that had tied earlier life to lakes and rivers. They could travel far into the interior, over terrain that would have been lethal to their amphibian ancestors. Among the reptiles, variety flourished. Some were small, fast, and insect-eating, moving with quick, efficient steps through the underbrush. Others were larger, heavy-bodied herbivores that grazed on the tough plants of the dry plains. A few became predators, lean, agile hunters that fed on everything smaller than themselves. The division of roles between herbivore and carnivore, between scavenger and ambush hunter, became clearer than ever before. The ecosystems of the Permian were beginning to resemble the ones that would later define the age of reptiles, though the creatures themselves were older, stranger, and less familiar to modern eyes. One group in particular stood out, the synapsids. These were not quite reptiles, though they shared many traits with them. They had evolved a single opening behind each eye socket in their skulls, a feature that allowed for stronger jaw muscles. This small structural difference gave them a powerful advantage. Synapsids could chew more effectively, process food more thoroughly, and regulate their metabolism better than their reptilian counterparts. Some, like Dimetrodon, grew large and developed distinctive sails of bone along their backs, which may have helped them control body temperature. Others remained small and agile, their bodies covered in thin skin or early forms of insulation. The synapsids were the distant ancestors of mammals, though that future was still far away. In the Permian, they were the dominant terrestrial vertebrates, spread across every habitable region of the supercontinent. Their dominance was not uncontested. Insects and arthropods occupied every niche of the smaller world, flying, crawling, burrowing and decomposing. Beetles, already present, diversified into many forms, their hard shells and efficient wings allowing them to thrive in almost any climate. Dragonflies, though smaller than their Carboniferous relatives, still ruled the air. Termites broke down wood, and early cockroaches filled the same roles they do today. These creatures formed the base of the land's food web, recycling nutrients and sustaining the reptiles and amphibians above them. Their ability to survive depended on their adaptability to heat and dryness. Many species developed thicker exoskeletons to prevent water loss, or shifted their activity to the cooler hours of dawn and dusk. The rhythms of life were no longer just seasonal, they were daily, bound to the temperature of the air and the movement of the sun. In the coastal regions and along rivers, amphibians still held on. The variety of species was smaller than in earlier ages, but their presence remained significant. Some grew to impressive sizes, becoming apex predators in freshwater environments. They waited in the shallows for reptiles and small animals that came to drink, their flat heads and wide mouths perfect for ambush. Others lived among vegetation, feeding on insects and using their strong limbs to crawl across mud and debris. The drying of the climate made these ecosystems unstable. Ponds and streams could vanish within weeks of drought, forcing amphibians to migrate or perish. Over generations, their populations moved toward areas where water remained reliable, toward the coasts, the deltas, and the margins of the great inland basins. Their gradual retreat marked one of the first great shifts in the distribution of life caused by long-term climate change. In the oceans, survival followed a different set of rules. The water, though more stable than land, was not free from stress. The Panthalassa was immense, but its circulation was uneven. Some regions teemed with life, while others stagnated under low oxygen. The creatures of the shallow seas thrived where sunlight and nutrients were abundant. Reefs built by sponges, bryozoans, and early corals formed the centre of marine ecosystems. Fish of many kinds filled the water above them. Sharks, bony fish, and armoured species descended from older lineages. Ammonites drifted through the currents, their coiled shells marking their slow spiral through the ages. Yet even in these fertile waters, adaptation was constant. Species developed new feeding strategies, new forms of locomotion, new defences against predators. The ocean, like the land, was in transition. In deeper waters, life depended on chemical energy rather than sunlight. Hydrothermal vents along mid-ocean ridges provided heat and nutrients for bacteria that lived off the minerals in the rising fluids. These microbes in turn supported entire communities of organisms adapted to total darkness. Crustaceans, tube worms, and mollusks flourished in places where temperatures and pressures would have destroyed most other forms of life. The survival of these creatures demonstrated the resilience of the biosphere. Even in the most hostile conditions, life found a way to adapt, to feed on the planet's energy in whatever form it appeared. On land, the behaviour of animals changed in response to the new conditions. Burrowing became one of the most successful strategies. Many reptiles and small synapsids dug into the soil to escape the heat, using tunnels as refuges during the day. These burrows also provided protection from predators and helped maintain moisture in dry environments. Fossilised burrows from this time show branching networks, chambers and nests, evidence of social behaviour and complex life cycles. Some animals shared their burrows with others, forming small communities that relied on cooperation to survive. These patterns of shelter and movement helped species persist even as the climate shifted around them. Reproduction also evolved to meet the challenges of the environment. The development of the amniotic egg was one of the most important adaptations in Earth's history. By enclosing the embryo in a protective shell and internal membrane, animals could reproduce away from water, freeing them to live in deserts, forests and mountains. This innovation, which had appeared earlier but became widespread in the Permian, allowed reptiles and synapsids to expand into every terrestrial habitat. The variety of reproductive strategies also increased. Some species laid eggs in buried nests, while others retained them internally until hatching. Parental care, still rare, began to appear in certain forms, an evolutionary step that would have lasting consequences for future lineages. Plants too refined their strategies for survival. In regions where fire was common, species evolved thick bark or cones that only opened after being heated. Their seeds were designed to sprout in ash-rich soil, taking advantage of the nutrients released by burning. In arid zones, plants developed long taproots to reach underground water or reduce their leaf surfaces to minimize evaporation. Some grew in seasonal cycles, sprouting rapidly after rare rains and lying dormant during droughts. These adaptations created new kinds of landscapes, open woodlands, scrub plains, and sparse forests that spread across the interior of Pangea. The interaction between plants and animals continued to deepen as herbivores fed selectively on certain species, influencing which plants dominated each region. The global network of life had reorganized itself around resilience. Ecosystems became more modular, less dependent on single species or stable conditions. When drought struck or fires swept through, life returned quickly once the immediate stress passed. The organisms that survived were those that could tolerate variation, those that could store energy, migrate, or reproduce flexibly. Even microorganisms played a part in this adaptability. Soil bacteria and fungi continued to break down organic matter, cycling nutrients and stabilizing the environment. Without them, recovery after disturbance would have been impossible. The Earth's biosphere functioned as a self-correcting system, where each species contributed to the stability of the whole. Predation continued to shape evolution. As herbivores grew larger and better armoured, predators developed stronger jaws and faster limbs. The arms race between hunter and prey drove the diversification of both groups. In the open plains, large synapsids hunted smaller reptiles, while amphibious predators ruled the rivers and wetlands. The fossil record from this period shows evidence of specialized teeth and bones adapted for specific diets. These changes mark the slow shift toward more complex ecosystems, ones that could sustain larger animals and more intricate food chains. Even in times of scarcity, evolution never paused. It simply adjusted its pace, fine-tuning existing forms to meet new demands. The distribution of species across Pangea reflected both geography and climate. In the tropical regions near the Tethys Sea, warm temperatures and seasonal rains supported lush vegetation and a high diversity of animals. Toward the poles, the environment grew cooler and less predictable. Forests gave way to open plains and eventually to tundra-like conditions where hardy plants clung to the thin soil. Migration became a survival strategy for many species, following favourable conditions as the seasons changed. Fossils show that some animals travelled great distances, their remains found in regions far from their usual habitats. These migrations, though slow in geological time, connected ecosystems across the supercontinent. The adaptability of life extended to its chemical processes as well. Organisms adjusted their metabolic rates to cope with temperature fluctuations. Some reptiles could lower their activity during droughts, entering states of torpor to conserve energy. Others relied on behavioural adaptations, seeking shade, changing feeding times, or using burrows to regulate temperature. The physiological flexibility of these creatures allowed them to survive in environments that changed more quickly than their bodies could evolve. In this way, behaviour became a bridge between biology and environment, allowing life to persist through cycles of stress and recovery. Over millions of years, these patterns stabilized into recognizable biomes: deserts, forests, river valleys, coastal plains, each with its own web of species and interactions. The interior deserts remained sparsely populated, dominated by reptiles and hardy plants. The coasts and river systems supported greater diversity, acting as refuges during dry periods. The balance between these regions shifted with the climate, but the overall structure remained intact. Life had found ways to occupy every available niche, even in a world that seemed determined to challenge it. Every adaptation carried a cost. Energy invested in protection or endurance was energy not available for growth or reproduction. Species balanced these trade-offs in different ways. Some produced many offspring, relying on numbers to ensure survival. Others produced few, but invested more care in each. Over time, these strategies determined which lineages would thrive and which would fade. The result was a biosphere shaped as much by constraint as by opportunity, a system tuned to survive, not necessarily to flourish. The resilience of the Permian world was remarkable, but it was not limitless. Beneath the surface, the same geological forces that had built Pangea continued to stir. Volcanic activity released gases that slowly altered the atmosphere, adding carbon dioxide to the air and affecting global temperatures. For the moment, the planet's systems absorbed these changes, maintaining equilibrium through weathering, vegetation, and ocean circulation. But the balance was fragile. The very adaptations that had allowed life to endure, flexibility, drought tolerance, efficient respiration, were preparing it, unknowingly, for a future where survival would be tested beyond anything it had experienced. For now, though, the experiment continued. The forest still stood, the desert still breathed heat, the oceans still moved, and life went on, adjusting to every challenge with the same patience it had shown since the beginning. The world did not end suddenly. The change began quietly, so gradually that no living creature could have recognised what was happening. The forest still swayed in the dry wind, the seas still carried their slow currents, and the continent still drifted almost imperceptibly beneath the same pale sky. But deep beneath that apparent calm, the planet's balance was shifting. The forces that had built Pangea were still moving, and the heat that had gathered under its massive crust was beginning to find a way out. In the far northern reaches of the supercontinent, where volcanic activity had long simmered in silence, the pulse of the Earth was starting to quicken. The first signs of change appeared in the air and the sea. The atmosphere, already warm and dry, began to hold more carbon dioxide. At first, the difference was small, barely measurable over centuries, but the effect compounded. Global temperatures crept upward, altering rainfall patterns and pushing already fragile ecosystems closer to their limits. Deserts expanded, creeping into regions that had once supported forests and rivers. The coasts, which had long served as refuges for life, began to experience irregular seasons and prolonged droughts. The monsoons grew less predictable, their timing shifting as the land and ocean warmed at different rates. The climate that had been extreme but stable was becoming unstable. The cause lay beneath the land, in the mantle that had been slowly heating under Pangea's weight. The crust, thick and insulating, trapped energy that had nowhere to escape. When the pressure became too great, the mantle began to melt in concentrated zones. Magma rose through weaknesses in the crust, spreading laterally until it reached the surface. What followed was not a single volcanic eruption, but an era of fire that would last millions of years. In what is now Siberia, a vast region of fissures opened in the ground, releasing torrents of molten rock that spread across the land in sheets hundreds of meters thick. These were not ordinary volcanoes. They were flood basalts, immense outpourings of lava that covered entire regions in layers that hardened into dark, featureless plateaus. Each eruption released massive amounts of gases into the atmosphere: carbon dioxide, methane, sulfur dioxide, and water vapor. These gases altered the planet's chemistry on a global scale. The carbon dioxide trapped heat, accelerating the warming that had already begun. The sulfur dioxide, on the other hand, formed aerosols that temporarily reflected sunlight, creating brief intervals of cooling followed by renewed warming. The result was a climate that oscillated violently between extremes. The atmosphere thickened with dust and haze, filtering sunlight and changing how heat was distributed across the planet. The air became unpredictable, the seasons disordered. The oceans, which had long buffered the atmosphere by absorbing carbon dioxide, began to reach their limits. As more gas entered the air, the water took in more of it, forming carbonic acid that lowered the ocean's pH. This acidification weakened the shells of marine organisms that relied on calcium carbonate for their structure. Corals, brachiopods, and many plankton species began to struggle, their growth slowing and their skeletons thinning. The delicate balance of marine chemistry that had supported vast ecosystems was being undone. At the same time, the warming atmosphere increased the temperature of the surface waters, reducing the oxygen they could hold. The great circulations that carried oxygen from the surface to the depths weakened, and regions of stagnant oxygen-poor water expanded. In these low oxygen zones, the conditions favoured certain bacteria that thrived in the absence of oxygen but released hydrogen sulfide as a byproduct. As their populations grew, the gas began to accumulate in deeper waters. Normally it would have remained trapped there, but as warming continued and ocean mixing declined, the boundary between oxygenated and anoxic layers moved closer to the surface. In time, hydrogen sulfide began to escape into the air, poisoning the atmosphere and killing oxygen-breathing organisms both in the sea and on land. The smell of sulfur would have filled the coastal winds, a warning to anything that breathed that the planet's balance was faltering. The effects of the Siberian eruptions were not confined to the region itself. The gases and particles they emitted circulated globally, carried by the winds into both hemispheres. Layers of ash settled across continents, leaving thin grey markers in the sedimentary record. Acid rain fell, leaching nutrients from the soil and washing them into the sea. Rivers became conduits for erosion, carrying minerals and toxins alike into the ocean basins. The land, once a patchwork of forests and plains, began to lose its vegetation. Without plant roots to stabilise it, soil eroded more easily, feeding a feedback loop of degradation. The skies grew dim and the air grew heavy with particulates that blocked sunlight while trapping heat. On land, the first signs of collapse appeared in the plant life. Many of the forests that had withstood drought and fire began to die back as conditions worsened. Increased temperatures and irregular rainfall made reproduction difficult for species that relied on seasonal cues. Fires became more frequent, fueled by dry vegetation and lightning storms triggered by volcanic ash. The once stable ecosystems fragmented into isolated patches of surviving flora. Conifers and cycads, which had dominated for millions of years, began to decline. The great red deserts of Pangea expanded, consuming what remained of the fertile lowlands. The surface of the supercontinent became a patchwork of dust and rock, its rivers reduced to shallow, intermittent channels that carried more silt than water. The animals that depended on those plants suffered next. Herbivores found less food, and as their populations dwindled, the predators that hunted them followed. Many species of large synapsids vanished from the fossil record within a few million years of the volcanic eruption's onset. The smaller forms, better able to survive on limited resources, fared somewhat better, but even they were affected by the instability of the climate. Reproductive cycles were disrupted, and migration patterns no longer matched the seasons. Eggs desiccated in the heat, and burrows collapsed under flooding rains that came without warning. Entire food webs unravelled as the environment became unpredictable. In the oceans, the crisis deepened. As anoxic conditions spread, the seafloor became a place of death. Layers of black shale formed where organic matter accumulated faster than it could decompose. Coral reefs collapsed, their delicate frameworks dissolving in acidic water. Trilobites, which had survived for hundreds of millions of years through every major extinction before this one, disappeared completely. Ammonites and brachiopods declined sharply, and the diversity of marine species plummeted. The once rich ecosystems that had filled the shallow seas turned into barren plains of silt. Even plankton, the foundation of the marine food web, declined in abundance, disrupting the chain of life from the smallest organisms to the largest predators. As the oceans became warmer and more stratified, the release of methane from seafloor sediments added another destabilizing factor. Methane hydrates, frozen combinations of water and gas, melted under the increasing heat, releasing vast quantities of methane into the water and eventually into the atmosphere. Methane is a powerful greenhouse gas, far more effective than carbon dioxide in trapping heat. Its release amplified the warming that the Siberian eruptions had already begun. The Earth's temperature climbed further, and the feedback loop accelerated. The warmer it grew, the more methane escaped, and the more the planet heated in return. This cycle, once started, was almost impossible to stop. The combined effects of volcanic emissions, ocean stagnation, acidification, and greenhouse warming began to alter the planet's carbon cycle beyond recognition. The balance between the sources and sinks of carbon broke down. Plants could no longer absorb enough carbon dioxide to offset what was being released. The oceans, saturated with carbon, could no longer take in more. The result was a runaway effect in which the atmosphere became increasingly hostile to life. The global average temperature may have risen by 5 to 10 degrees Celsius, enough to transform ecosystems completely. Polar ice vanished, sea levels fluctuated, and rainfall patterns shifted again. The distinction between climate zones blurred as extremes spread everywhere. The fossil record from this interval shows a dramatic decline in biodiversity. In some regions, as much as 90% of marine species disappeared. On land, roughly 2/3 of all vertebrate families vanished. The extinction unfolded over several million years, but in geological terms it was nearly instantaneous. It was the most severe mass extinction the Earth had ever experienced, and its causes were not a single catastrophe, but a chain reaction of interconnected stresses. The planet's internal heat, released through volcanic eruptions, had triggered a cascade of atmospheric and oceanic changes that reshaped every environment on Earth. Even as the crisis deepened, some life forms endured. Certain species of burrowing reptiles and amphibians survived by retreating underground, where temperatures were more stable. In the oceans, a few hardy lineages of ammonites, bivalves, and microscopic plankton managed to persist in the least affected regions. Their survival depended on luck as much as adaptation. Areas near upwelling currents, where oxygen still reached the surface, became refuges. The species that lived there would become the ancestors of future ecosystems, carrying forward the resilience of life even as most of the world fell silent. The atmosphere during this time would have been strange and heavy. Volcanic gases filled the sky with haze, tinting the sunlight a dull red. Ash and dust lingered for years after major eruptions, scattering light and cooling the surface temporarily before the greenhouse gases reasserted their dominance. The alternation of cooling and warming stressed ecosystems further, preventing any long-term recovery. Plants that tried to regrow after fires or droughts were wiped out again by sudden frost or heat. The stability that life had relied on for millions of years was gone, replaced by cycles of stress and collapse. The land itself reflected this turmoil. Sedimentary layers from the end of the Permian are marked by evidence of erosion and sudden deposition. Floodplains turned into barren mudflats. River systems shifted their courses frequently, leaving behind abandoned channels filled with silt. The red beds of this era became even more widespread, their colour deepened by oxidation in the dry, oxygen-rich atmosphere. In some areas, fossil soils show evidence of intense weathering, suggesting long periods of drought punctuated by short, violent rains. The planet's surface was unstable, reshaped by the same forces that were killing the life upon it. For the organisms that remained, survival depended on flexibility. Small size, generalized diets, and tolerance for extreme conditions became the traits that determined success. Large animals, which required more food and stable climates, were at a disadvantage. In the oceans, microscopic life began to shift toward forms that could withstand acidity and low oxygen. These survivors formed the foundation of recovery after the extinction, though that recovery would take millions of years. The ecosystems that emerged afterward were not the same as those that had vanished. They were simpler, dominated by species that could thrive in unstable environments. The Permian extinction was not a single event but a drawn-out transformation. Each phase of environmental change triggered another, and together they pushed the planet past a threshold. It was the culmination of processes that had been building for millions of years: the gathering of heat beneath the continents, the rise of volcanic activity, the alteration of atmospheric chemistry, and the feedback loops of climate and ocean circulation. Once the system crossed that point, it moved toward a new equilibrium, one that few existing species could tolerate. The Great Dying was not just an end. It was the turning of the Earth's systems toward a new mode of operation, one that would eventually lead to the world of the Triassic and the rise of new forms of life. The record of this time is written in every continent. In the rocks of South Africa, Russia, and China, layers of fossilized remains show abrupt transitions from abundance to emptiness. Shell beds end suddenly, replaced by barren sediment. In coal-bearing strata, the thick seams of carbon-rich vegetation give way to thin, discontinuous bands, signalling the collapse of the forests. The diversity of fossils within each layer drops sharply, replaced by only a few hardy species that managed to survive. These geological witnesses tell the same story from different corners of the world, a planet overwhelmed by its own internal forces, struggling to regain balance in the face of its own heat and chemistry. Even in this era of collapse, the continuity of life never broke completely. Bacteria continued to cycle nutrients in the soil. Fungi decomposed the dead forests, releasing carbon back into the air and preparing the ground for whatever would come next. Some small reptiles and amphibians endured in isolated pockets, feeding on what remained of the insect populations. In the oceans, microbial mats spread over the seafloor, filling the void left by lost ecosystems. The Earth had been stripped of much of its complexity, but not its vitality. The systems that maintained its habitability, weathering, circulation, photosynthesis, still functioned, weakened but unbroken. The Great Dying had begun, but the world itself was still moving, still breathing, waiting for the next cycle of renewal to begin. The planet had grown unstable. What had once been a vast and dry but steady landscape had become a furnace. The Earth was releasing the heat it had trapped for millions of years, and it did so through fire. Lava rose from fractures that split the crust in lines that stretched for thousands of kilometers. The land that had been forest and plain became black, its surface turned to stone, its air filled with smoke. The eruptions in the far northern reaches of Pangea continued without pause, one flow of molten rock following another, covering valleys, hills and rivers. Each eruption released more gas, more heat, and more ash, feeding the chain of changes that had already begun. The scale of these eruptions was beyond any human comparison. Entire regions melted. The Siberian Traps, as the formation would one day be called, spread across an area larger than modern Europe. The lava did not erupt from a single mountain or cone, but from cracks that opened in the crust like wounds. Magma poured out in waves that travelled for weeks before cooling, forming basalt plains that stacked layer upon layer until they reached thicknesses of several kilometres. The land glowed, the air shimmered, and the skies above filled with aerosols that reflected sunlight by day and trapped heat by night. Each eruption brought a different consequence. When the lava broke through layers of sedimentary rock rich in coal, oil, or limestone, it vaporized them instantly. The carbon and methane released from this process entered the atmosphere, amplifying the greenhouse effect already set in motion. When the lava met groundwater, steam explosions shattered the crust, spreading fine ash into the stratosphere. This ash circled the planet, dimming sunlight and producing brief periods of cold before settling back to the surface. The alternation of cooling and heating became a rhythm that destabilized the climate even further. Plants that tried to regrow after the cooler periods were scorched or buried during the next wave of heat. This cycle of destruction became continuous. The volcanic gases changed the chemistry of the air and water. Sulfur dioxide reacted with moisture in the atmosphere to form sulfuric acid, which fell as acid rain. It burned leaves, dissolved minerals, and poisoned lakes and rivers. The runoff carried metals and toxins into the ocean, where they interfered with the delicate balance of marine ecosystems. At the same time, the carbon dioxide released by the eruptions continued to accumulate. The atmosphere thickened with greenhouse gases, and the Earth's temperature climbed to levels that may have exceeded anything in its previous history. As the planet warmed, the land dried even further. What vegetation had survived the earlier phases of instability now faced the heat directly. Droughts became longer, the soil hardened, and dust storms swept across the interior of Pangea. Fires ignited spontaneously, sparked by lightning or the intense heat itself. They spread across the dry plains, consuming everything in their path. Without moisture, they burned hotter and faster, leaving behind only ash and blackened wood. The smell of smoke became a constant part of the air. Even far from the centres of eruption, the atmosphere carried traces of burning forests. The fires released more carbon into the air, intensifying the warming yet again. The skies over much of the world darkened. Thick clouds of soot and aerosols blocked sunlight, creating long periods of twilight. Photosynthesis slowed, weakening the food chain from its base. The plants that survived in isolated pockets could no longer sustain the herbivores that depended on them. The loss of vegetation accelerated erosion, sending more sediment into the seas and burying coastal habitats. The oceans, already struggling with heat and acidity, grew murkier. The once clear shallows turned cloudy with silt and dead plankton. Coral reefs dissolved, and the seafloor became coated in fine layers of ash and organic debris. In the marine depths, the conditions worsened. As oxygen levels fell, vast portions of the ocean became anoxic. The boundary between oxygenated and depleted waters rose higher each year, until much of the continental shelf, where most marine life had once thrived, became uninhabitable. The release of hydrogen sulfide from the depths continued, spreading into the atmosphere and poisoning the air near the coasts. This gas also destroyed ozone in the upper atmosphere, allowing more ultraviolet radiation to reach the surface. The combination of heat, toxicity, and radiation created an environment where few organisms could survive for long. On land, the chain of extinction spread. The large synapsids that had ruled the Permian plains, creatures that had once seemed invincible, disappeared from the record. Their populations declined steadily as their prey vanished, and the heat exceeded their ability to regulate body temperature. The smaller reptiles, those able to burrow or live in shaded environments, held on longer, but even they faced dwindling food sources and rising temperatures that left little refuge. Insects, once abundant, declined sharply as the plants they fed on died out. The quiet hum that had filled the air for millions of years faded, replaced by the sound of wind and the crackle of distant fire. The temperature increase during this period was extreme. Global averages may have risen by more than 10 degrees Celsius in only a few 100,000 years, a blink in geological time. The equatorial regions, already hot, became nearly uninhabitable. The polar zones, which had once been temperate, grew warm and ice-free. Rain patterns collapsed. Instead of predictable seasons, storms came irregularly, bringing floods to regions that had been dry for centuries and leaving other areas without rain for decades. The old climatic order was gone, replaced by chaos. The Earth had entered a new state, one where its feedback systems no longer stabilized but amplified each other. Each generation of life faced a world slightly worse than the one before. Population shrank, species disappeared, and ecosystems collapsed from the bottom up. The loss of biodiversity was not just a count of vanished forms, it was a breakdown of the processes that sustained life itself. With fewer plants, less carbon dioxide was removed from the atmosphere. With fewer animals, nutrients were no longer cycled efficiently through the soil and ocean. The feedback loops that had once balanced the planet began to work in reverse. The Earth was consuming its own stability, and fire was the mechanism of that consumption. In some regions, the lava fields continued to spread. The Siberian traps erupted in pulses that lasted for hundreds of thousands of years. Each pulse released new flows that covered the older ones, renewing the heat and emissions. The landscape that emerged from these eruptions was alien. Vast plains of black basalt that stretched to the horizon, still warm from the last flow, with cracks that glowed faintly in the dim light. Rivers were diverted or buried, lakes boiled dry, and entire ecosystems disappeared beneath the molten rock. The air shimmered with heat long after the eruptions ended, and the ground trembled from the constant movement beneath it. The atmosphere during these times was dense with haze. Sunlight scattered through the particles, turning the sky a dull orange or deep grey. Temperatures fluctuated violently between short cooling phases after major eruptions and long warming phases as greenhouse gases accumulated. Each oscillation put additional stress on the few remaining survivors. Plants that adapted to warmth were killed by cold. Species that endured dryness were drowned by sudden storms. The planet's instability meant that no environment remained consistent long enough for recovery. The chemical composition of the ocean continued to change. As carbon dioxide dissolved into the water, the acidity increased further, dissolving shells and coral skeletons faster than they could form. The once diverse marine communities were reduced to a handful of tolerant species. Algae blooms, fed by nutrients from erosion and decay, occasionally turned the water green or red, depleting oxygen even more. These blooms produced toxins that spread through the food web, adding another layer of stress to an already collapsing system. The surface of the sea, once alive with light and movement, became flat and quiet. Beneath it, the water turned stagnant, its colour darkening with suspended matter and microbial decay. On the continents, heat reshaped the surface itself. Rocks expanded and cracked under the constant temperature fluctuations. Rivers carved new paths through layers of volcanic ash and dust. Lakes evaporated, leaving behind salt flats that glared white under the sun. The red deserts of Pangea deepened in colour as iron in the soil oxidized in the dry air. The horizon became hazy with heat, the outlines of mountains distorted by the rising waves of energy radiating from the ground. Even without fire, the landscape burned in its own way, glowing with reflected sunlight and heat trapped by the thickening atmosphere. The air carried more carbon dioxide than at any time in the planet's recent history. Its concentration was likely several times higher than modern levels. The greenhouse effect from this concentration was powerful enough to alter global circulation patterns. Winds slowed as temperature differences between poles and equator diminished. The reduced circulation weakened ocean currents further, deepening the stagnation that already plagued the seas. The planet's systems, once interconnected and dynamic, became sluggish and uneven. Energy accumulated instead of dispersing, and that accumulation made each change more destructive. The collapse of the forests accelerated the transformation. Trees and plants that had taken millions of years to spread across the supercontinent were gone in less than a geological instant. Without their roots, the soil turned to dust easily lifted by the wind. Dust storms carried particles across continents, dimming the sky even in regions far from the volcanic centres. These airborne minerals settled into the oceans, changing their chemistry yet again. The link between land and sea, once a source of balance, became another pathway for disruption. Even as the world burned, life did not vanish completely. A few ecosystems clung to existence in isolated pockets. In high latitudes, where temperatures were still moderate, small forests of hardy conifers persisted. Along the coasts, shallow lagoons and estuaries sheltered organisms that could tolerate variable salinity and temperature. In caves and underground burrows, animals found refuge from the heat and toxins above. These survivors endured because they were small, adaptable, and resilient. They required little, and they could wait for long periods in unfavourable conditions. Their persistence was not triumph, but continuity, the maintenance of life's thread through an age of destruction. The air at times may have been thick enough with smoke and gas to make breathing difficult, even for the hardiest of creatures. Hydrogen sulfide and carbon dioxide pooled in low areas, suffocating anything that wandered into them. Acid rain stripped nutrients from the soil, while ultraviolet radiation from the weakened ozone layer burned the exposed surfaces of plants and animals. Even the insects that once dominated the planet's air disappeared almost entirely. The Earth had become an environment that tested the limits of biology. The volcanic phase that drove this transformation continued for more than 1 million years. With each passing century, the cumulative effect deepened. The feedback between the atmosphere, the oceans, and the land ensured that no single factor could be isolated. Every element of the planet's system, its heat, its air, its water, its living organisms, was tied into one vast network of cause and consequence. The fires were not merely eruptions of molten rock, but manifestations of the Earth's internal energy reaching the surface, transforming everything it touched. Eventually, as the last major pulses of volcanism subsided, the heat that had been released into the air and sea remained. the planet's temperature did not immediately fall. The greenhouse gases persisted, trapping energy long after the eruptions ended. The recovery would take millions of years, but the damage was already complete. The ecosystems that had defined the Permian were gone. The forests had burned, the reefs had dissolved, the synapsids and amphibians had mostly vanished, and the oceans were nearly devoid of complex life. The world had been remade by fire, stripped down to its essentials, left waiting for new forms to arise in the aftermath. The surface of Pangea, seen from above, would have appeared scarred and lifeless. Black plains of basalt stretched across the north, red deserts covered the centre, and pale salt flats lay where lakes had once been. The coasts were fringed with lifeless shallows, their water tinted green or brown from decay. The air shimmered with heat, and the light of the sun, filtered through a haze of aerosols, cast everything in muted tones of gold and red. The atmosphere was dense, the wind sluggish, and the silence deep. It was a planet in transition, still alive but altered beyond recognition. And yet, beneath that silence, the same processes that had always sustained Earth continued. The mantle still moved, the core still generated its magnetic field, and the ocean still circulated, even if slowly. The planet's internal energy, the same force that had caused the eruptions, would in time also contribute to renewal. Volcanic activity would decline, weathering would draw carbon dioxide back into rocks, and temperatures would gradually stabilize. The fire that had consumed the world would eventually give way to recovery, just as the Earth had recovered from earlier cataclysms. But for now, the planet remained in its fiery phase, its surface reshaped, its air transformed, its life reduced to a few enduring threads. It was still breathing, though every breath carried the heat and ash of its own upheaval. The heat that had once gripped the planet began slowly to fade. The great volcanic eruptions that had reshaped the northern regions quieted over generations. The mantle still moved beneath the crust, but the relentless pulse of molten rock finally eased. What remained was a world covered in layers of basalt, ash, and dust. The air, though still thick with greenhouse gases, began to clear as the eruption subsided. Rain returned in irregular patterns, washing the soot from the sky and carving new rivers through the cooled lava fields. It would take millions of years for the planet to recover, but even in its silence, the first traces of renewal had already begun. At first, the change was almost invisible. The land remained barren, the ocean stagnant, and the temperature high. The chemical balance of the atmosphere was still altered by the carbon released from the eruptions. But within that harsh environment, small processes resumed. Wind carried fine dust across the plains, and the dust settled in cracks and hollows where moisture collected. Rain mixed with volcanic ash to form thin soils, poor in nutrients but capable of supporting the simplest forms of life. Microbes were the first to return. They colonized the cooling lava and the exposed sediments, feeding on the minerals released by weathering. Their presence began the long process of transforming stone into soil again. In the oceans, the recovery followed a similar pattern. The water remained warm and low in oxygen, but the chemical reactions that had driven the earlier collapse started to reverse. As the atmosphere cooled and volcanic emissions decreased, the temperature difference between surface and deep waters increased again. Slowly, the ocean circulation revived. Fresh oxygen entered the upper layers, and mixing began to restore the balance that had been lost. The first organisms to reappear were the microscopic ones, cyanobacteria and plankton that could tolerate the altered chemistry. They formed the foundation of a new food web, releasing oxygen and drawing carbon dioxide from the air through photosynthesis. The clarity of the water began to return, a faint sign that the seas were breathing again. On land, the first visible plants appeared in isolated regions where water was more reliable. Small ferns and seed plants grew in the cracks of rocks and along the edges of rivers that had carved their way through the ash. Their roots anchored the loose soil, holding it in place against wind and erosion. Over time, their decay added organic matter, improving the ground for the next generation. The process was slow and uneven. Whole regions remained barren for tens of thousands of years, while others developed patches of green that spread outward season by season. The world was rebuilding itself piece by piece through the persistence of simple organisms that required almost nothing to survive. The air, though still warmer than before, began to stabilise. With the end of large-scale volcanic outgassing, the concentration of greenhouse gases gradually declined. Weathering of the basaltic rocks drew carbon dioxide from the atmosphere, locking it away as carbonate minerals. This natural feedback helped cool the planet, though the process took millions of years. Each rainfall contributed, dissolving small amounts of carbon dioxide and carrying it into rivers and oceans, where it was buried as sediment. Slowly, the equilibrium that had been lost during the Great Dying was re-established. The recovery of life was not a return to what had been. The extinction had cleared entire ecosystems, and the species that survived were few. The new biosphere began from the remnants that had endured in sheltered regions. Small animals that could tolerate extremes, plants that reproduced quickly, and microbes that could survive almost anywhere. These survivors spread into the empty niches left behind, evolving rapidly to fill them. The world was quiet, but it was not empty. The faint sound of wind through sparse vegetation and the movement of water through new channels marked the beginning of another cycle. Among the first vertebrates to reappear in abundance were the smaller reptiles and amphibians that had survived in burrows and along coasts. Their populations expanded as new vegetation provided shelter and food. Some evolved into new forms better suited to the changing conditions. The synapsids that had once ruled the Permian returned in smaller, more specialized varieties, many of which showed early signs of the traits that would later define mammals. They were no longer the large predators or grazers of the past, but small, quick animals with efficient metabolisms and flexible diets. Their ability to adapt to varying environments allowed them to thrive where others could not. The insects also returned, though their diversity was far lower than before. Beetles, flies, and early relatives of modern grasshoppers and crickets recolonized the land as plants spread. Their presence helped restore the cycle of decomposition and pollination. By breaking down dead plant material, they accelerated the formation of soil and released nutrients that sustained new growth. The relationship between plants and insects, once disrupted, began to rebuild itself. Each generation made the environment slightly more stable, preparing it for the slow return of complex ecosystems. In the oceans, the first signs of renewal came from the plankton that formed the base of the food chain. As they multiplied, they supported small invertebrates and fish that fed on them. Coral reefs, which had vanished entirely during the crisis, began to reappear in shallow, well-oxygenated regions. The new reefs were different, built by different species, adapted to the warmer and more variable conditions. Crinoids, mollusks, and ammonites diversified again, taking advantage of the newly opened ecological spaces. The oceans, once dark and depleted, grew brighter with life as each layer of the food web reassembled. The recovery of marine ecosystems helped stabilize the climate even further. As plankton drew carbon dioxide from the atmosphere, they sequestered it in the deep ocean when they died. The carbon cycle resumed its natural rhythm, balancing the exchange between air, land, and sea. The planet's systems were reconnected, though still fragile. Each new generation of organisms contributed to the rebuilding of the biosphere, adding resilience through diversity. The land that had once been covered in fire now carried the first forests of the new age. Conifers and seed ferns spread across the coasts and uplands, their roots penetrating deeper into the soil. Their canopies provided shade, reducing surface temperatures and allowing moisture to accumulate. Streams that had once been choked with ash cleared, flowing steadily through valleys that were beginning to support more complex life. Amphibians returned to these waterways, their calls echoing in the humid air. Insects filled the space between water and land, and small reptiles hunted them in turn. The food webs that had vanished began to reform, linking species together once more in cycles of energy and survival. The atmosphere's oxygen level, which had dropped during the extinction, began to rise again as plants and plankton spread. The air grew clearer, and the haze that had once dimmed the sunlight faded. The colour of the sky returned to a lighter blue, and the surface of the planet cooled enough to allow more stable weather patterns. Rain became regular again in certain regions, feeding rivers and replenishing lakes. Where there had been deserts of red dust, there were now patches of vegetation that grew a little larger each century. The Earth, though scarred, was beginning to look alive once more. The pace of evolution accelerated during this time. With so many ecological niches empty, natural selection favoured rapid change. New forms appeared, each slightly more adapted to the conditions than the last. Reptiles diversified into groups that would later dominate the Mesozoic world. Amphibians, though fewer than before, continued to occupy the wetlands and shallow waters. In the oceans, early ancestors of marine reptiles emerged, their bodies streamlined for swimming. The evolutionary experiments of this era would shape the next 250 million years of life on Earth. The foundations of future ecosystems, the dinosaurs, the mammals, and the modern oceans, were laid during this slow renewal. The geological processes that had once brought destruction now became agents of recovery. Erosion wore down the volcanic plateaus, carrying minerals into the sea. These nutrients fertilized the oceans, supporting plankton growth and accelerating the restoration of marine ecosystems. Weathering of basaltic rock continued to draw carbon dioxide from the air, cooling the planet further. The interplay between land and sea re-established the cycles of carbon, oxygen and water that defined Earth's stability. Each process worked in concert with the others, transforming chaos into order once again. The scars of the extinction remained visible in the rocks. Layers of ash and black shale marked the boundary between the old world and the new. Fossils of once abundant species ended abruptly, replaced by the remains of their successors. In some regions, the transition was sharp. In others, it was gradual, a record of local recovery. These strata formed the dividing line between the Permian and the Triassic, a moment in geological time when the Earth began to rebuild itself after its greatest loss. The planet's surface recorded every step of that renewal in stone, preserving the evidence of destruction and rebirth side by side. For millions of years, the global environment remained unstable but improving. Temperatures stayed high but no longer rose uncontrollably. Rainfall increased, and the deserts began to shrink along their margins. Vegetation spread into new areas, and soils deepened as organic matter accumulated. Rivers carved networks that connected mountains to the sea, transporting sediments that built deltas and coastal plains. These new landscapes became centres of diversity, where life flourished in forms that had never existed before. The Earth's surface, once barren and scorched, was once again a mosaic of ecosystems. The slow cooling of the atmosphere encouraged the return of seasonal patterns. Regions that had experienced only extremes of heat and drought began to experience predictable cycles of wet and dry, warm and cool. Organisms adapted to these rhythms, timing their growth and reproduction to the changing conditions. Forests expanded during the warm, wet seasons and shed their leaves during the dry. Animals migrated with the rains or entered dormancy during lean times. The synchronization of life with the planet's cycles returned, restoring a balance that had been absent since the height of the volcanic activity. In this restructured world, the boundaries between the old and new forms of life blurred. Many lineages that had survived the extinction evolved into unfamiliar shapes. The synapsids gave rise to new species with more efficient metabolisms and differentiated teeth. The reptiles diversified into the ancestors of crocodiles, lizards, and eventually dinosaurs. In the oceans, ammonites, bivalves, and new coral species expanded again, rebuilding the reefs. The biosphere was smaller and simpler than before, but it was vigorous. Evolution worked quickly in the absence of competition, filling the empty ecological space left by the Great Dying. The recovery was not uniform across the planet. Some regions remained barren for much longer, especially those covered by the thick basalt layers of the Siberian traps. Others, like the coastal margins of the Tethys Sea, recovered faster, their climates moderated by the nearby water. These variations created isolated environments where species evolved independently, increasing diversity over time. What began as survival gradually became innovation. Life adapted not just to endure but to explore the possibilities that the New World offered. As the Triassic period took shape, the Earth's systems regained stability. The carbon cycle balanced, the oceans circulated freely, and the atmosphere settled into a more consistent state. Temperatures cooled enough to allow forests to cover much of the land once more. Rivers ran year-round, and the seas became rich with oxygen and nutrients. The planet had emerged from its longest and deepest crisis, transformed but alive. The life that returned was not the same as before, but it carried forward the legacy of endurance that had defined every age before it. Even in its recovery, the memory of the catastrophe remained etched into the planet's processes. The geological cycles that regulate temperature, weather, and chemistry now bore the imprint of what had happened. The balance between volcanic outgassing and carbon sequestration was more finely tuned. The biological feedbacks that stabilized climate had become stronger through the resilience of the organisms that survived. The Earth had learned, in a sense, to maintain its equilibrium more effectively, having passed through an extreme that tested the limits of its stability. The new world that emerged from the ashes of the Permian was the foundation for the Mesozoic, the age that would see the rise of the dinosaurs, the diversification of marine life, and the eventual evolution of mammals and birds. Every living thing that followed owed its existence to the survivors of the Great Dying, to the microbes that recolonized the lava, the plants that took root in the ash, and the small animals that found shelter underground. Their quiet persistence ensured that the planet's story continued. The process of recovery did not erase the past, but built upon it. The layers of basalt, the oxidized red soils, and the fossilized remains of vanished species remained as a record of what the Earth had endured. Each new generation of life lived upon the remnants of the old, transforming them into the basis of the future. The Earth had burned, suffocated, and nearly lost its capacity for life, but it had not stopped. From the first microbial films on cooling rock to the return of forests and the slow reoxygenation of the oceans, the planet demonstrated again the continuity that defines it. Renewal was not a single event, but a long sequence of adjustments, each one guided by the same principles that had always governed the world: adaptation, persistence, and time. And so, the silence that followed the fire gave way to sound again. The wind through growing forests, the flow of water through new rivers, and the faint hum of insects returning to the air. The light filtering through the atmosphere was clearer now, the sky bluer, the temperature bearable. The world had survived its most severe test, reshaped but enduring. The land that had been turned to ash was green once more, and the oceans that had turned dark now shimmered with life. The Earth had entered a new age, its surface carrying the scars of the past, but also the quiet certainty that life, once established, does not easily let go. The world that rose after the Great Dying was one rebuilt from fragments, but its foundations were still the same. The landmass that had once been Pangea remained enormous, stretching almost from pole to pole, a continent so vast that it still defined the way wind, ocean, and life moved. Though its forests were young and its ecosystems new, the planet still bore the outline of that ancient union. The memory of the supercontinent lived in the structure of the Earth itself, in the shape of the continents, in the rocks that carried traces of its assembly, and in the air that had changed with its birth. For millions of years after the Permian ended, Pangea continued to dominate the planet, Its coasts outlined the great Panthalassa on one side and the Tethys Sea on the other. Its interior remained dry, its climate governed by the same slow circulation of air that had shaped the deserts of earlier ages. The volcanic heat that had once broken through its crust had quieted, but the mantle beneath still moved, its convection currents pressing and pulling on the plates from below. The forces that had assembled the supercontinent were already preparing to undo it. The separation would not begin for tens of millions of years, but the first fractures were already forming, small invisible faults deep beneath the crust, opening in silence. The surface above these deep processes continued to evolve. The rivers that once carried ash and sediment now cut through solid basalt, revealing layers of history with every passing year. The mountains that had formed when Pangea came together began to erode, their peaks slowly rounded by wind and rain. The minerals that weathered from those rocks entered the oceans, nourishing plankton and contributing to the recovery of life. The slow interaction between the solid earth and the living surface continued, just as it always had, linking geology and biology in one continuous system. As the ecosystems matured, the landscape took on new forms. Forests spread across temperate regions, forming belts of green that followed rainfall patterns. Swamps and lakes returned to lowlands, providing homes for amphibians and early reptiles. Insects filled the air again, pollinating plants and recycling organic matter. On the plains, small reptiles and synapsids hunted, burrowed, and scavenged, their lives driven by the rhythm of light and temperature. The planet had reached a new equilibrium, one that would sustain the rise of entirely new lineages of life. The ocean too had transformed. The warm, shallow waters of the Tethys became centres of evolution. Reefs flourished again, built by new species of corals and sponges. Fish diversified, filling ecological niches that had been empty since the extinction. Ammonites spiralled through the open seas, their coiled shells marking the slow passage of time in layers of sediment. Each generation added calcium, carbon, and life to the ocean floor, rebuilding the marine world one molecule at a time. The deep waters, once stagnant, circulated freely again, carrying oxygen to the depths and allowing complex organisms to thrive. The ocean that had suffocated now supported abundance. Pangea itself remained a single body of land, but its immensity influenced everything around it. Winds carried heat across its surface unevenly, creating vast monsoons on the eastern coasts and dry winds over the western plains. The interior remained a region of extremes, scorching during the day, cold at night, and marked by long stretches without rain. The coastal regions closer to the oceans were more temperate, their climates softened by the sea. These contrasts shaped the evolution of life across the continent. Species that lived along the coasts adapted to humidity and seasonal cycles, while those in the interior evolved to withstand heat and drought. The diversity of environments led to the diversification of life itself. The memory of the supercontinent persisted in the way the planet's crust bore its weight. The mantle beneath Pangea continued to convect, and the thick crust of the continent trapped heat. Over time, this trapped heat began to weaken the crust, forming rifts that extended slowly across the land. These rifts were the first signs of separation. They marked the future boundaries of what would become the Atlantic Ocean and other seas that would split the continents apart. For now, the cracks were narrow, filled with sediment and occasional volcanic activity, but they were the precursors of motion. The Earth was never truly still, and even in its quietest moments, it was preparing for change. The animals of this new age carried the legacy of survival in their design. The reptiles diversified into groups that would eventually dominate the Mesozoic. Some remained small and agile, feeding on insects and plants. Others grew larger, with limbs and lungs adapted for efficient movement on land. In the oceans, the first marine reptiles evolved from land-dwelling ancestors, taking advantage of the recovering seas. They swam with bodies built for endurance, feeding on fish and ammonites. These forms of life were different from those that had come before, but they were built on the same biological principles: adaptation, efficiency, and persistence. The synapsids, though diminished, continued to evolve quietly alongside the reptiles. Many were small nocturnal creatures, their bodies covered in thin insulating layers that helped them retain heat. Their teeth had become more specialized, their jaws capable of precise chewing, and their metabolisms more stable. These subtle changes were early steps toward the traits that would later define mammals. In a world that favored endurance over dominance, these small survivors found their advantage in flexibility and energy control. They lived in the shadows of the larger reptiles, but would one day inherit the world again. The plants that spread across Pangea's surface continued to shape the atmosphere. Through photosynthesis, they drew down carbon dioxide, cooling the planet and restoring oxygen levels to stable values. Their roots broke down rock, contributing to soil formation and nutrient cycling. Forests became reservoirs of carbon and water, moderating temperature and precipitation. In this way, the vegetation helped regulate the same climate that sustained it. The feedback between life and environment, interrupted during the extinction, was now functioning again. Each forest, each river valley, was a living mechanism of balance. Even as life stabilized, the planet's memory of what had come before remained written in its layers. The black shales and red beds of the late Permian continued to mark the boundary between eras. In them were the signatures of the collapse, carbon isotope shifts, ash deposits, and the fossilized remains of extinct species. These records preserved the chemical and biological history of the catastrophe, a permanent reminder of how deeply the Earth's systems were connected. Every layer above them told the story of recovery, showing how new forms had emerged from old patterns. The planet itself was the archive, its rocks the pages, its surface the record of motion and renewal. As the Triassic progressed, the continents began to feel the first hints of motion away from each other. The rifts in the crust widened slowly, filling with water and volcanic material. Lakes formed in these depressions, and as they expanded they connected to form new seas. The separation of Pangea was beginning, though imperceptibly. Over millions of years these rifts would open into oceans, dividing the supercontinent into the northern landmass of Laurasia and the southern landmass of Gondwana. The breakup of Pangea would reshape global climate again, redistributing heat and moisture around the planet. But in the memory of the Earth, the imprint of its union would never fade completely. The mountain ranges that had formed when Pangea came together still stood, their roots deep in the crust. Over time, erosion would wear them down, carrying their sediments across the continents and into the sea. These sediments would form new rocks, new layers in the geological record. The cycle of construction and erosion, of assembly and dispersal, continued without end. The forces that had built the supercontinent were the same that would eventually destroy it, and the fragments that resulted would someday collide again to form new supercontinents in the far future. The memory of Pangea was not just historical, it was structural, encoded in the rhythm of the planet's interior. The pattern of life followed this same rhythm. Extinction and renewal alternated in long cycles, each one leaving behind traces that influenced the next. The organisms that evolved after the Great Dying carried within them the genetic and ecological legacy of those that had come before. Their forms reflected the pressures of the past, the heat, the drought, the instability. In that sense, Pangea lived on not only in the rocks and the continents, but in the biology of the creatures that inhabited the new world. Every adaptation was a response to conditions created by the supercontinent's existence. Every success and failure traced back to the systems it had set in motion. The oceans surrounding Pangea bore the signs of its influence as well. The currents that circled the Pantalassa and the Tethys had been shaped by the continent's mass. When the land began to break apart, those currents shifted, creating new pathways for heat and nutrients. The marine life that evolved during this time reflected those changes. Species adapted to one ocean found themselves isolated in another, driving further diversification. The memory of the supercontinent was preserved in the distribution of life, in the shared ancestry of species separated by oceans that did not yet exist. Even the air carried its legacy. The atmospheric patterns established by Pangea's size and shape left lasting effects on the planet's climate. The alternation of monsoons, the cycle of wet and dry seasons, and the distribution of deserts all began with that configuration of land and sea. As the continents drifted apart, those patterns evolved but never disappeared completely. Modern climates still bear echoes of those ancient systems. The red deserts of Africa, the seasonal rains of Asia, and the prevailing winds of the Atlantic all trace part of their origin back to the age when the world was one. The long-term influence of Pangea extended beyond climate and biology to the structure of the Earth's crust itself. The collisions that formed it thickened the continents, strengthening their cores. Those stable cratons still exist today, forming the foundations of modern continents. Beneath the shifting surface of the Earth, those ancient rocks remain, largely unchanged since the Permian. They are the physical remnants of the supercontinent's body, the solid evidence that it once existed and shaped everything above it. In time, as the Triassic gave way to the Jurassic, the world would look entirely different again. The breakup of Pangea would open new oceans, create new coastlines, and alter the flow of air and water. Life would continue to diversify, filling every niche opened by change. Dinosaurs would rise, dominate, and evolve into birds. Mammal ancestors would persist quietly in the background, refining their warm-blooded physiology. The world would grow green and fertile again, and the scars of the great dying would fade beneath new forests and new reefs. But beneath it all, the memory of the supercontinent would remain. Every continent that drifted apart carried a piece of it, both in its rock and in its geological identity. The Earth's cycles would continue as they always had. Supercontinents would form and break apart again, perhaps 5 or 6 times more over the planet's lifetime. Each one would bring its own arrangement of climate and life, its own rise and fall of species. Yet the lesson of Pangea would persist in every one of them, that the planet's unity and division are both temporary, that stability and change are inseparable. The memory of that ancient continent is not simply a geological fact, but a reflection of how the Earth itself operates, through endless movement, through destruction and renewal, through the slow shaping of everything by the forces beneath and the air above. And so the land that had once been joined now began its long drift apart, its fragments destined to become the continents we know. The mountains that had risen when they collided would erode, the seas that surrounded them would change, and life would continue to adapt. But in the deepest structure of the planet, and in the continuity of its living systems, the memory of Pangea endured. It remained in the alignment of the continents, in the flow of ocean currents, in the composition of the atmosphere, and in the quiet, constant movement of the crust. It was the imprint of unity on a planet that never stops moving, a reminder that even the most immense creations of the Earth are temporary, yet their influence lasts for eons. The world that emerged from the Permian carried both the scars and the strength of what had come before. Its landscapes were new, its life different, but the patterns remained the same. Continents joined, broke apart, and joined again. Oceans opened and closed. Species evolved, vanished, and evolved again. The Earth continued its long, unbroken cycle, and within that cycle, the memory of every age remained. The memory of Pangea was one of those layers, a record not just of rock and motion, but of the resilience that defines the planet itself.